So let's say in BGP, we have discussed, let's say we have R1 here, we have R2 here, we have R3 here, we have customer edge device, and we have customer edge here, and here we are running OSPF. This has a route 1.1.1.1.1. This has a route 2.2.2.2.2. Okay, and here we have EBGP, and here we have EBGP. Okay, and in between R1, R3 we have IBGP. Okay, and we have done a redistribution from EBGP to IGP protocol, that is OSPF. Same here, we have done a redistribution from EBGP, a BGP to IGP, that is OSPF. Okay, so R2 will receive 1.1.1.1.1 route, R2 will also receive 2.2.2.2 route, correct? Via BGP. Right or wrong?
Yeah, right.
Okay, so now if I do a ping from this device to 2.2.2.2.2 with source address 1.1.1.1.1, so in this case the traffic will go to R1, the traffic will go to R2, R3, and finally it will reach to CE, right? So in this case the control plane and the forwarding plane will reach end to end, correct? Will not be having any issue in this case. So if we are running this network, everything is reachable, why we need MPLS then? Why MPLS? So this is a provider routers, right? So this is my core router, that is ISP. Okay, these are the customer routers, and yes, everything is reachable now. Okay, using that redistribution. So why MPLS? So if any customer is using this diagram, so what you can offer and what you can explain to the customer, like you have to use this feature MPLS and this will be the benefit. Any idea? Anyone?
Actually, to make core routers are free. For that reason, we are using MPLS for like
Okay, just
in
wait. The
MPLS.
first thing you're saying, it will make these core routers free, right?
Yes.
BGP free basically.
Okay, we are not using any BGP here still, right? We are just using IGP. Okay. Okay, so that's the first benefit. Okay, the second one.
To run multiple we use my MPLS.
Sorry. Spark, your voice is bit.
No, not I am actually. I think someone
Okay,
else is speaking.
okay.
Not I am.
Hello.
Hello. Can you hear me, guys?
Hello. Am I audible?
Yes.
Yeah,
Yes. Now you're audible. Yeah.
Can you? Am I audible to you?
Yes, now you're audible.
Yeah. In this scenario, for customers, we need to use the MPLS.
Mm-hmm.
Actually, your voice is not audible. It is like robot voice only.
Okay, no worries. Spark, any other idea? The second benefit, what we can have here?
I think, sir, we can free like control plane traffic will not pass through that. I think so, because BGP is not.
Plane. That will reach end to end definitely every time, because we have a neighbor spin between R1 and R3 directly, right? So they can exchange control plane. Okay.
Okay, then let's go. I don't have idea more about it.
Okay, so first of all, if I'll use here MPLS, right, the first thing, these core routers will be available to add other routes, right? They will never maintain the customer routes, correct? So my routers will be free. They will not maintain any customer route. So that's the first benefit, right? If I'll talk about the second one, okay, so as you're saying, we can have multiple customers, right? So if we have multiple customers on the same router, yes, those are possible. But right now, if we have multiple customers here in this case, right? So maybe let's say the customer 1 is having a subnet 10, the customer 2 is also having the same subnet. So what will happen there? Those subnet will be same at that time, correct? So this router will get confused, okay, to which device I have to send the traffic for this 10 subnet, right? But using MPLS L3VPN in this feature, what you can do, you can have multiple customers on the same router, right? I'll explain how. The third thing, what we are doing here, once I will use MPLS, I will remove the redistribution, correct? So if I will remove the redistribution, what we can have, a benefit we can have, will not be having suboptimal routing, right? So in this case, what will happen here, all the routers will be using the same path to go to reach to the neighbor, to reach to the destination, right? The fourth thing, if we have multiple edge routers, if we are not using MPLS, we are using only distribution, and if we have multiple edge routers, so what we can have here, we can have a loop also, right? So if we are using some different kind of redistribution, some wrong redistribution with wrong metric calculation, right? In that case, we can have a loop. So these benefits we can have if we are using MPLS, okay? One more thing here, whenever we send the IP packet, a normal IP packet, what happens, all the devices will check the layer 1, layer 2, layer 3, right? So all the routers will do a lookup till layer 3, but once I'll be using MPLS, what will happen at that time, the device will never go to layer 3. They will just check 1, 2 and that MPLS header and just pass that packet to another router. Same 1, 2 MPLS will pass the traffic to another, same 1, 2 MPLS then pass the traffic to another. It means in the core network, they will never check IP packet, never, okay? So using this one, the device will route the packet much faster than IP packet, okay? So I hope these benefits are clear, right? So while implementing MPLS to a new customer, you can explain the benefits and the features that you are going to use, okay? So just tell me any doubt till this point.
No, for me, no.
Okay.
Neeraj, can you explain this last point, fourth one, loop?
Okay. For the loop prevention, if I draw a diagram, like we have a core network. Okay, we have n numbers of router. We have 2 edge devices here that is connected to customers. Then again, we have 2 edge devices here connected to customers. Okay, so if we are just performing redistribution on these routers, right? So whenever we have more than 2 points of redistribution, okay, and we are doing a redistribution into the core, then we can have a loop here. Okay. So sometimes what happens, let's say we have a route from this customer that is 1.1.1.1.1. The device will share the traffic to this one, right? Same, I can get the route via this one, and again I'll do a redistribution here. So in this case, we can have a loop. Okay.
Yeah, got it.
So if we have 2 points of redistribution, so definitely we can have a loop. Okay.
Suboptimal routing also that will
Yeah,
happen.
definitely. Suboptimal routing and loop. Suboptimal definitely will be having suboptimal, but loop, sometimes we can have loop, sometimes not. Okay, that's depend on the redistribution, how you have done the distribution. Okay. Multi-protocol label switching. Okay, so first of all, let's understand the VPN model. So before these things, basically what we were doing, we have 2 types of VPN model. One is overlay VPN model and one is peer-to-peer VPN model. Okay, so I'll draw a diagram for this overlay. Let's say this is ISP. Okay, that is connected to a customer. Same here, that is connected to a customer, right? So if we have overlay VPN model, so in this case, what happens here in this condition, this ISP will provide a lease line connection, end-to-end lease line. It means bandwidth will be reserved from this user for this user end-to-end. Okay, let's say we have a link of 100 MB. It means that 100 MB will be reserved for this user throughout the network. Okay, if that is using anything, that is sending some information, not sending, that doesn't matter. This bandwidth will be reserved for this special user. Okay. So in this condition, in the overlay VPN, what we use, this is just a name, overlay VPN. What we use here, we use lease line connections. Okay. Now, if I talk about peer-to-peer model, what happens in this condition? Basically, what we have here, just one single router, one customer, and that have a complete lease line end-to-end. Okay. If I talk about peer-to-peer model, we have two things here in the peer-to-peer model. One, that is shared approach, and one is dedicated approach. Okay, so in the shared approach, let's say we have one provider as router and we have multiple customer as router. Okay, so in this condition, these customers will be using a single PE device to reach other sites. Okay, so in this condition, what we can use here, let's say we have a switch here. I want to use a single PE router to connect these devices. I can connect via a switch, right? And via this port, and I can use here sub interfaces to make them reachable, correct? So if we have shared approach, so what we can do, we can use this kind of feature, sub interfaces, right? If we have dedicated, it means, let's say a customer wants a dedicated link, right? A dedicated approach in peer-to-peer VPN model. So what happens in that condition, if we have 4 customer, CE, so they will be having a separate router PE to reach to other sites, or they will be having a separate interface to a single PE. Okay, so this is dedicated approach, and we have one thing that is shared approach. So right now in our diagram, in the practicals, what I'll show you here, I'll show you this shared approach, because dedicated, that is too simple, right? I'll be having a just single link, one single router, and just need to configure some protocols or BGP, and we'll share the routes. But in the shared approach, what we will be having, we'll be having a switch, we'll connect the customer devices, we'll connect the PE devices, we'll configure some VRF, we'll configure some sub interfaces. It means one single VRF for each sub interface, and we'll try to make the communication possible to the other customers. Okay, so this is just a VPN model. So any doubt in this one?
No, the scenario is clear to me. Actually, a little bit doubt. People are saying that no, that underlay VPN and overlay VPN. Actually, I saw that you written here overlay VPN. What is underlay VPN then?
Okay, underlay, look, what we do whenever we run a BGP, right, the underlay protocols will be IGP protocols, correct?
Yeah, correct.
So if I talk about IGP protocols, so those routers are using some, let's say, any path they are using, right? Or any other combination we are using, let's say we are using some GRE tunnels there, right? So those things we can count as the underlay VPN, okay? But in MPLS, whenever you configure MPLS, what we do always, we use these kind of approaches, overlay VPN or peer-to-peer model, okay? So these things we use here, and we can say just these things we use in the MPLS, okay? The underlay we never use in MPLS, the underlay. That is a kind of IGP. So IGP is type of underlay protocol. So if we're using some other features in the IGP, those we can count as underlay, okay?
Okay, okay.
Any other doubt to this point?
No, no.
Okay. one thing we have to make the customer reachable that we don't use, but yes, we have a concept that is EVN. What is EVN? Easy Virtual Network. Okay, so in this one, what we do, we basically reserve a path for a user. How we reserve that path? Let's say we have R1 here, we have R2 here, we have R3 here. Okay, and we have one customer here, that is customer 1. We have customer 2 here, customer 1.1 and customer 2.1. Okay, and we have one single link in between these devices. So what this concept says, if you have this kind of diagram and you want a communication from this user to this user and from this user to this user, and right now I don't want to use any special feature like MPLS, BGP. I just want to use a feature that is EVN. Okay, Easy Virtual Network. So what we do here basically, we use VLAN feature here to send information from one customer to another customer separately. How? What I'll do here, I'll configure these interfaces as trunk. Okay, how I can configure these interfaces as trunk? Just to configure, I'll configure here sub interfaces. Okay, so I'll configure here .1, .2, same here .1, .2, .1, .2, .1, .2, like this I'll configure. Okay, and I will say these two are the part, this interface and this interface is a part of one single VRF. Same here, this interface and this interface will be the part of single VRF. Same here, this interface and this interface will be the part of single VRF, and same I will do for these interfaces. Okay, it means what we'll be having here, we will be having a path, a special path for this customer and one special path for this customer. And yes, we need a routing protocol to make that reachable, right? So once I'll configure VRF, once I'll configure sub interface, and using those things, once I will configure routing protocol, the customer will be having a reachability to this customer using the same path, and same here, this customer will be having a reachability to this customer using the same path. And this is called, this feature is called EVN. So once anyone talk about EVN, what is EVN? So this is the concept and theory that we have for the EVN, Easy Virtual Network. Okay.
Okay.
So the practical we'll do later. Once we start the practicals, I'll show you the practical here, but this is very simple. We just need to configure some VRF, some sub interfaces, and this task will be achievable. Okay.
Is there having any kind of limitation related to VLAN? How many VLAN we can
No,
create over there?
we can configure n numbers of here. Okay.
Okay, sir.
All the VLANs we can use here. If we have 10 customers, 20 customers, 30 customers, so yes, we can configure. So basically that's up to your sub interfaces. How many sub interfaces you can configure? Okay.
For every VLAN, we need to create a separate sub interface.
For separate sub interface, we need to have one single VLAN like this. Okay.
No, suppose we have a 20 customer. So
Okay.
in that case, we need to create 20 sub interface.
Yes, definitely. That is mandate.
Okay.
Because first of all, whenever I will receive a traffic from any customer from here, I have to define a VRF first of all, and have to configure the same some sub interfaces just to reach other neighbor. That's it. Because over this link, let's say as you're saying, we have 20 customers, right? So over this link, we have to send 20 customer routes, but these are the routers, right? Manually, we cannot configure globally the trunk port and the VLANs, right? That's why we have to configure 20 sub interfaces, and they will be carrying the traffic with the VLAN information. Okay.
Okay, sir. Means we have a very short scenario. We have a less number of customer. Only in that scenario we can use.
Yes. That's why this is the name is EVN, Easy Virtual Network.
Okay, sir.
Hello.
Mm-hmm.
I'm
Yeah.
not able to configure a sub interface. What will happen to all the VLANs?
You're not able to configure sub interface.
Yes, I'm not.
What are the
Not
commands?
configure sub interface. What will happen network that is virtual?
No, sorry. What are the commands that you're using to configure sub interfaces?
Configure VLAN, configure like virtual. I'm not configure virtual. That is sub interface. What will happen
No, in that case, basically, again,
in that case?
first of all, let's say you are saying like I will not configure any virtual interface here, right? These things we are not configuring.
Yes.
So this router will not be able to send a specific traffic to R2 for a specific destination. Okay, that will be a big issue. It means these routers will be maintaining a single routing table and that will be having everything. It means that will be a bit confusing if, let's say, this has a route 1.1.1.1.1 and same the customer 2 has the same information. So this device will always route a packet to C1 or C2. Okay. So in that case, we'll be having a single routing table and that's not a use case. Okay.
Basically, like when R1 is connected with the C1 and we are configuring the sub interface over there, then it will come with a .1 queue. So .1 queue tagging, and
yes,
the router will further not forward it that .1 queue because it will not able to segregate the traffic, right?
Okay, no. Basically, first of all, I have to configure .1 queue. Okay, that is fine. But that will still in the routing table, in the global table. Then we have to configure VRF. Okay. Sub interface. Then we have to specify the VRF. Okay. Then we can run the protocol. So like this, we have to use the steps. Okay. Sub interface, then a different routing table, and then a protocol over the routing table. Okay. Like this, we have to configure. If I will just configure some interfaces and running a protocol globally, the result will be same. Okay.
It will not segregate the traffic from customer A to customer B actually.
Yeah. Okay. So any other doubt here in EVN?
Okay. Okay.
All good? Guys, any doubt? Anyone?
No. Going good now.
Good.
So right now we'll discuss the packet forwarding. Okay, how the devices receive a packet and how they will forward the packet. Okay, in a normal IP packet. So first we'll discuss what will happen once a device will receive a normal IP packet, and then we'll discuss what will happen once they will receive the MPLS labeled packet. Okay, so right now, first of all, we'll discuss the switching mechanism. Okay, in the switching mechanism, we have three things. One is process switching. The another one is fast switching. The last one is safe. Okay, so first we'll start with the process switching. So let's say we have R1 here that is connected to a user. Same here, we have another user here. So this we are talking about the process switching. Okay. So let's say this user have a subnet 10.0.0.1. Okay, this user have an address 20.0.0.2. And here we have .2 and here we have .1 for these same subnet. Okay. A router will be having two things. One is RP, route processor, and one is SE, that is switch engine. Okay, route processor will handle all your control plane. Let's say we have a protocol that is RIP, EIGRP, OSPF, any protocol, and they are exchanging updates. So this route processor will maintain those things, will track those things, and will receive the information and will put those information into the routing table. It means getting an update, putting that update in the routing table as a best path. So these tasks RP will do, route processor. And then let's say we have a subnet 10, 20, 30 in my routing table using RP, right? What switch engine will do? Switch engine will find the ARP entries for those subnet. Like let's say we have 20 subnet, we have 30 subnet, we have 40 subnet. So now in the ARP table, switch engine will put ARP table. If I want to go to 20, what is the best exit interface and what will be the MAC that I have to use to send the packet out to this interface? Same for 30, same for 40. So that's a normal mechanism. Now, let's say this user is sending 1000 packets. to this user. Okay, so the first packet, so the device is sending a ping packet. Let's say the source is 10.0.0.1, the destination is 20.0.0.2. okay, the source MAC, here we have A, here we have B, here we have C, and here we have D. Okay, so right now that will use a source MAC, that is A. The destination MAC will be B right now because that's a router. Okay, and the devices will send the packet out to the interface. Now R1 will receive the packet over this interface. Now what R1 will do? The first thing, R1 will get the packet and will hand over to switch engine. It means what will happen here, very first time switch engine will receive the packet. So whenever a router gets a packet, in actual the switch engine will receive the packet. Okay, so right now the switch engine is having that packet. Okay, what this will do, switch engine will remove the layer 2 information. So what it will remove? It will remove those MAC addresses A and B. Okay. The third thing, what it will do? Switch engine, now switch engine is having a clean IP packet without any layer 2, right? Switch engine will hand over that packet to route processor because the route processor will be having information how to reach 20.0.0.2, correct? So switch engine will hand over that packet to RP. Now what RP will do, this route processor will check routing table, or we can say it will do a lookup in routing table and will find the best exit interface to reach that subnet, the destination subnet, right? Basically the route processor, the routing table, we can say that's maintain our network, not a route. Okay. The fifth, once RP find the information, RP will hand over the information and packet to switch engine. So now switch engine will receive the information. So switch engine will get layer 3 packet with those IP information and best exit interface to route the packet. Okay. Now what switch engine will do? Switch engine will check ARP entry to find MAC address for given interface. So let's say R1 is saying that E0 by 0 is my exit interface, is the best interface to reach 20.0.0.2, right? The switch engine will find, okay, to E0 by 0, what MAC address we have to use in the source, what MAC address we have to use in the destination, so that the device will do this lookup, the switch engine will do this lookup and will put, finally, switch engine will add new layer 2 header that will be having C and D, right? C and D, and will send the packet out to PC. Okay. So this happens for a single packet, and what will happen in this condition, once R1 will receive the second packet, it means R1 will repeat the same process for all 1000 packets. So in this case, what will happen here? The R1 will receive all the packets that will handle everything. It means what happens here? RP is responsible to maintain routing table, or we can say to handle control plane. Okay, and is also responsible to forwarding plane. So in this case, what we can have, the device can be down, the RP can be down, right? because right now what is happening here, the switch engine is responsible basically to do this kind of forwarding, but RP is doing the forwarding. It means RP is handling every single packet to do the forwarding, right? Because right now the switch engine does not have a special power to maintain anything or to forward the packet directly to PC. Okay, so this is the process switching. So if on a router we have process switching, so this will be the behavior to route a packet. Okay, then we'll discuss after this one. We have fast switching. Okay, so the same diagram I'll be using here in the fast switching. We have R1. Okay, again we have two things. One is RP, one is switch engine. We have one PC here, another PC here we have that has the same subnet 10.0.0.1. This has a subnet of 20.0.0.2. Okay, and same, this user want to send 1000 packets to the another PC. So what will happen here? Again, I'll start from the first step, and let's say the user MAC address is A, B, and here we have C, and here we have D. The same thing it will do. The first of all, R1 will receive the packet. Now we can just put the line. Switch engine will get the packet first. Okay, switch engine will remove the layer 2 info. Okay, the third thing, switch engine will hand over the packet to RP just to find the destination interface, the best interface to send the packet out. The fourth thing, RP will find the best exit interface, or we can say it will do a lookup
online
in routing table. Okay. And then RP, guys, can you please mute?
okay sir, sorry.
So RP will hand over the information to switch engine. So in this case, what will happen here? The router is repeating the same steps as we did in the process switching. Okay, but now one more thing it will do. Switch engine will get the information and will maintain the cache entry for the information. So let's say the information is toward the subnet, you have to use E0 by 0 interface. Okay, so this entry, this information, the device, the switch engine will maintain in the cache entry. Okay, and the seventh step, switch engine will add a new layer 2 info and will send it to another PC. So this was the process for the first packet. Process for first packet. Okay, now what will happen for the second packet and for the rest of the packets? The first step, switch engine will get the packet and will remove layer 2. Switch engine will check the cache entry and will find the best exit interface, and then what it will do, switch engine will add new layer to info and will send the packet out to another PC. So now in this case, what is happening here? RP is responsible to handle only first packet of the flow, and the remaining switch engine will handle those things, right? Because right now what main thing here we have, switch engine is able to maintain cache entry for the information we can see. Okay, so in this condition, in the fast switching, the device is able to maintain, the switch engine is able to maintain a cache entry for the same information, and once it will receive the packet, it will just remove the layer 2, will check the entry, will add new layer 2 information, and will route the packet. And this is basically called as packet rewrite. Okay, so whenever anyone asks what is packet rewrite, so yes, this process is called as rewrite, packet rewrite. It means once a device will receive a packet, it will remove layer 2, will check the information, will add a new layer 2, that's called as packet rewrite. Okay, so this is a behavior that we have in the case of fast switching. But what will happen here if we have 1 lakh flow? So RP will handle 1 lakh data packets. Okay, so the fast switching works on the flow. If we have 10 flows, so that RP will just check 10 first data packet, and then the switch engine will start working for those. Okay, now finally what we have here, switch engine, sorry, the CEF, Cisco Express Forwarding, okay. So in this condition, we have one special table, that is CEF table. What happens in this condition? This is something different. So let's say we have R1 that has a RP and that has a switch engine. Okay, so whenever this RP will receive the information, let's say the RP is getting some routes, 10 route, 20s route, 30s route. So what will happen here? The RP will just send a mirror copy of these information to CEF table. So now the CEF table will just maintain a mirror copy of my RP, whatever routes they have. But in the CEF table, before putting the routes in the CEF table, the device will do a final lookup. Okay, or we can say that is a recursive lookup if we have. Okay, so the device will just put the IP, the destination IP, the best exit interface, and if we have a next hop, that it will put the next hop also. So this will be having IP, the destination IP, the best exit interface. So once we have the same user, the user want to send 1 lakh packet, let's say. Okay, we have 1 lakh users, that doesn't matter. Whenever this device will receive the information, R1 will receive the information, the device will remove layer 2 information, will check CEF table, will add new L2 information, and will route the packet. It means now RP will never handle any data plane packet. So in the CEF, Cisco Express Forwarding, what the device will do, the device will just remove the layer 2, will add the layer 2, and will check the CEF table to route the packet. That's it. Okay, so only in this case of CEF, the device will never check RP. It means that RP will never check the data plane packet, never. It will just maintain, it will just handle the control plane. Okay, so this was for the IP packet. Okay, now if let's say we have R1 here, we have R2, and we have R3 here. Okay, so if I talk about the IP packet, so what will happen here? All of these routers will go till layer 3, right? So the RP will check the layer 3 information and will route the packet. But once we talk about the labels packet, what will happen here? Let's say R1 is getting a packet that is 1.1.1.1.1 and the destination is 3.3.3.3. So they will be having some labels, right? So let's say the layer 2 MAC address A and B that has a label 16. Okay. Then we have some IP addresses. Now, whenever R1 will receive the information, it will just remove this one, will replace the label. Let's say now it will put 17 here and will route the packet. Once R2 will receive the information, it will remove the layer 2, will replace the label, will send it to R3. Let's say that is 18 now. R3 will do the same thing. It will remove the layer 2, will check the label, will replace the label and will forward it to another neighbor. So in the label packet forwarding, what happens in the background, the devices will never check the layer 3. Okay, it means what we have here, the devices, they are saving time to check layer 3 information. Okay, they will just route the packet using the label. Okay, so that's why if we have label switching, the devices will do the fast switching here in this case. So any doubt in this condition? So we have multiple.
So what is the difference between like this CEF and fast switching?
Sorry, come again.
So what is the difference between the CEF and fast switching? I mean, we have the CEF. So CEF is like it will.
In the fast switching, the device will depend on the flow, number of flow. If the flow break, then and in that condition, let's say we have 1.1.1.1 and the destination is 2.2.2.2 and the interface is E0 by 0. So this is a flow, we can say. Okay. So once this flow breaks, or if an interface goes down, anything happens, if the flow break, then again, whenever the device will send the packet out to this destination, RP have to check the first data packet. Okay. But in the CEF table, that doesn't matter how many flow we have, how many packets we have, RP will never check any data packet. Okay. This is the benefit.
Okay. So I mean, only once RP will check to make this CEF. And after that, there is no timeline. I mean, if the flow is broken and
no,
for unlimited time, it will see.
Yeah, look, in CEF, RP will never check the first packet even. Okay, because in CEF table, we have RP, we have switch engine. Whenever RP will receive any kind of information in the routing table, what it will do, it will send a mirror copy to CEF table. Okay. It means now no need to go to the manager, just go to this guy, check the information and send the packet out. That's it. Okay, like this. So the CEF table will be having a mirror copy of RP. Okay. We have a
okay. I mean, CEF has that capability which RP has.
Yes, exactly same. Correct.
Okay.
Sir, in CEF case, recursive lookup happen for every packet or it's on a flow basis?
Okay, basically whenever the CEF table will put the route in the table, before putting the route in the table in the CEF table, it will do a recursive lookup for that route. Okay, let's say.
Suppose we have 1,000 packet in that scenario.
Yeah, let's say. That doesn't matter how many packets we have, how many data packets we have. Basically, let's say we have RP. Okay, that is having some routes. The 10 route is reachable via 20. The 20 route is reachable via 30. The 30 route is reachable via 40. And the 40 route is reachable via E0 by 0. So before putting these routes, because now we have 4 routes, correct? 10, 20, 30, 40. So before putting these routes into the CEF, it will do a lookup in this table only, in the routing table. It will check, okay, 10, that is 20, but no, that is not an exit interface. Again, how to reach 20, that is 30. Again, that is not an exit interface. 30, that is 40. 40, yes. Now I find an exit interface. Now what CEF table will be having? If I want to reach 10, E0 by 0 is the best path. Again for 20, 30 is not the best interface. 40 is not the best interface. Yes, E0 by 0 is the best interface. To reach 20, E0 by 0 is the best. Same for 30 and same for 40. It means CEF table will be having a final best interface to send the packet out. It means routing table, this RP, will do this recursive lookup and will put the best information in the Ceph table. Okay.
Okay. So means suppose I am establishing a connection from source to destination. In Ceph table we have a best entry. So we are going to route 1000 packet. Once it will check that to reach the destination, I have a exit interface E0Y0. So it will not do any kind of recursive lookup and all these things for the rest of the packet, right?
Yeah, that's a one-time process only for the RP. The RP will be responsible for this recursive lookup and will just put the best information in the Ceph table. That's it.
Okay, thank you.
Okay, any other doubt?
Maintain that layer two address also, because here you assume that only layer 3 exit interfaces, right?
Sorry.
So where those Ceph actually see in fast switching and that packet switching, that there is a different mechanism, right? That route processor is adding that layer 3 address, and for MAC address there is a separate SE or something is there, no?
Is switch engine correct?
Switch engine. But in case of safe switching, from where it will get the MAC addresses actually?
Okay, yeah, the switch engine is working in the background, yeah.
Switch engine
Yeah,
also
basically
working.
the switch engine is just to maintain the data plane, okay? That will receive the information, will find the MAC addresses and will handle the data plane, okay?
So still by using safe, we are also using that connection. Sorry, that.
Yeah, basically the whenever
switch,
if you
right?
want to get some MAC addresses, right? The switch engine will work for that always, okay?
Always.
That is a real task of switch engine, okay?
Okay. Along with the safe, that switch engine also work in case of
Definitely, yes,
switching.
yes.
Okay then.
Because this switch engine is removing those things, right? Removing the layer 2, adding the new layer 2, and will the device is just checking the Ceph table, not RP, okay?
Okay. Then safe only the replicate of the routing table, right?
Yes,
It don't have
but
any MAC
Ceph has the
information.
best information, okay? In routing table, we can have a lookup like this, but if I talk about the Ceph, that will be having the best information, okay? If let's say we are running a fast switching and routing table have these information, so whenever it will receive a packet for 10, it will take time to do a lookup 10 20 20 30 30 40 40 E0 by 0, then it will send the information to switch engine. But if I talk about Ceph, it will just go to okay 10 E0 by 0, go out like this, okay?
Okay, in case of RP, multiple time that route lookup will happen, but in case of safe, only one time that route lookup will
Yes,
happen.
yeah.
Okay.
Okay, any other doubt in these things?
What are all the lookups this step will do?
Sorry?
What are all the lookups this step will do? Only destination IP it will see, or what?
Yeah, only destination, yeah, definitely.
Even though in routing table also you are looking for that destination only.
Yeah, basically the routing table always maintain a destination route, right? A destination network, sorry. Any other doubt till this point?
No, sir, no doubt.
No, sir.
Okay. So now we'll discuss the labels about the MPLS header and these things. Okay. So any idea about MPLS header?
Hmm. 20 bit I think reserved for the label, and 8 bit for TTL, 1 bit for
Okay.
QS I think. Bottom of stack
Okay.
or something.
Let us discuss first of all the label processing. Okay. So initially, let's say if I talk about the size of a label. So the size of a label is 20 bit. Okay. So we can have 2 to the power 20 and then we can find the range of that labels. Okay. So we have a size that is 20 bit, right? So we can have n numbers of here labels, right? So now we'll discuss how the routers generate some labels, how they find the best path, how they do a forwarding for the data plane using some labels. Okay, let's say we have R1, we have R2. Okay, just a minute. We have R1 that is connected to R2. Okay, that is connected to R3. That is connected to R4. So right now I'll just take an example in linear topology. Okay, then I will move to a rectangular or circular. Okay, where they will be having the multiple best path. So right now they will be having a single best path to reach each other. Correct. So let's say R1 has an information that is 1.1.1.1.1. R2 will be having a loopback address that is 2.2.2.2. Same R3 will be having, same R4 will be having.
Sir, I have lost the audio actually. I'm not able to hear you.
1.1.1.1.1.
Sir, voice break हो रही है आपकी.
Sorry.
Actually, we have lost your voice. I'm not able
Guys,
to
just give me a minute.
My voice is fine, I think. I mean, for me it is okay.
Sorry.
I mean, they are talking about the voice. I am getting the voice clearly. So I'm not sure. Like, maybe they have internet connection.
Yeah, I hope everyone is getting the voice now, right? I'm audible to everyone.
Yes, now.
Yes.
Yes, please.
So we have a route 1.1.1.1.1. Okay, same 2.2.2.2. We have 3.3.3.3. We have 4.4.4.4. And these are the loopback addresses of R2, R3, and R4. It means once I will run a protocol here, any routing protocol, so all the routers will be having the same database, correct? I think that is clear to all of you. If I will run a protocol here, so all the routers will be having the same database, right or wrong? That is
Right,
correct?
sir. Yeah, correct.
Yes.
Now, so let's say we have configured MPLS. Okay, the way the commands that we have used, I'll explain later what command we have to use and how they will originate those things and what will be the sequence. Okay, so right now let's suppose R1, R2, R3, R4, they are creating some labels. So the first thing, whenever we enable MPLS on a router, they originate labels locally. Okay, so R1 will originate a label locally. So let's say R1 is originating for 1, 2, 3, and 4. So this is just example. In future, I'll just modify some labels here. Okay, so just for the example, R1, let's say originating a label that is 10, 20, 30, and 40. R2 is originating a local label 40, 50, 60, 70. R3 is also originating a label, local label 80, 90, 100, 110. Same R4 is originating a label, that is local label 120, 130, 140, and 150. So let's suppose these are the local labels, okay, for these routes. Now, what they will do in the background, the devices will exchange these labels. So R2 will say, to reach 1.1.1.1, please use a label that is 40. Same it will say for 20, that is 50, that is 60, that is 70. So this is my remote label and this is my local label. Okay. So all the routers, first of all, will create a local label, and whenever they will receive a label for any specific route, that will act as a remote label. Okay. Same R1 will say to R2 10, 20, 30 and 40. These are the remote labels. Same R3 will say my remote labels are 80, 90, 100, 110. Same R2 will say to R3 my local labels are, for R3 that will act as remote label, 40, 50, 60, 70. Same R4 will send the information. The remote label will be 120, 130, 140 and 150. Same R3 will share the information to R4. Remote labels are 80, 90, 100 and 110. So this is the table. Once we run the protocol, once they will be having an MPLS neighborship, right? They will exchange the labels like this. It means first of all, they will create the local labels. Then they will exchange the labels to another router, and for another router, those labels will act as a remote label. So till this point, if you have any doubt, just tell me.
No, sir.
So this label is.
Yeah, please go ahead. Please go ahead.
Sorry, come again.
Label is kind of tag identification, like we were using in this redistribution to identify particular prefix or root. So it is the same, right? To identify
Kind of, yeah.
prefix or root. Huh?
Yeah, kind of.
Okay, kind of.
Okay, so this label is like decided once the packet come for the first time, right? So this R1 has decided that for 1.1.1.1, the label will be 10, right?
Yes, yes.
So how like they have defined this label and all, and how they are exchanging?
Sorry, how they are, what you're saying?
Yeah, how they have defined like this is the label for this, and how they are exchanging. Like for an example, if I talk about like in OSPF, they used to exchange hello packets. So in this case, how they have defined the label and how they are exchanging.
Okay, so basically in the background, as I told you, like they will be running MPLS LDP. Okay, how they will run LDP, that thing I'll discuss later. Okay, because in the background in LDP, they will be having some packets to exchange these information. Okay, so right now, this is just a proof or example that they will be using these things. Okay, what will happen here? Randomly, R1 will start a sequence. So this is just example, but they will always start from 16, 17, 18, 19. Okay, in the real, R1 will start from 16, 17, 18, 19. R2 will also start from 16, 17, 18, 19. It means all the routers will start from 16, 17, 18, 19. Okay. But just to get a clarity, I have used a different information, different numbers for all the routes. Okay. So they will be in the sequence, they will start from 16 in the real case, but right now this example, that's why I'm taking a different number just to get a clarity on this one. Okay. So
actually,
the
we
routers
cannot control these level.
Tell me.
As I'm saying, these level we cannot control. It is router generated. It will generate router automatically, right?
The routers will just check the routing table. Whatever information they will be having in the routing table, they will start doing a process. Okay, we have 10 routes. It means we have to allocate 10 labels for those routes. Okay. If routing table finds 100 routes in the table, they will allocate 100 labels for those routes. Okay, like this. This is a random process, or we can say this is an automate process. Once we enable MPLS, the device check, okay, I have 10 routes in my routing table, so I have to create a label, I have to add a label for each specific route. Okay, this is clear now. So first of all, they will create a local label. It means right now these routers have 4 routes. That's why they are creating local label 10, 20, 30, 40, 40, 50, 60, okay, this is, okay, no worries. 40, 50, 60, 70, 80, 90, 100, 110, 20, 30, 40, 50, right? So these are the local labels. And once they will, be having the local labels, they will try to exchange with the neighbor. So let's say the neighborship in between 1 and 2 is successful, right? They will exchange the information to each other. If you want to go to 1.1.1.1.1, use a label 40. And R1 will also say, if you want to go to 1.1.1.1 via me, use a label 10. Like this they will say. Okay. So till this point, they have exchanged the labels, right? Now I will show you how they will find the best path. Okay. Till this point, any doubt? A spark, any doubt?
No, sir. For me, it is clear.
Okay. Now, just to find the best path, what they will do basically, whenever they will put some labels, they put the exit interface or a next hop IP also. So as I told in the routing table, they will be having the best path, right? Let's say to reach 44444, they have a best path that is via R2. Let's say R2 is checking up information 444 they want to reach in the routing table, right? And the best path will be via R3, correct? It means R2 will automatically get to know this label is the best label to reach 4444. So they basically, the router will, once they will create this information, or we can say that is LFIB. Okay, label forwarding information base. Once the device will create a label forwarding information base, LFIB, okay, they will put the route, they will put the local label, they will put the outgoing label, that is remote label, as a best label. They will not put the both labels. They will say, okay, 110 is the best label. Okay, and how the device find that as best label? Due to FIB. In the FIB, they will be having just routes without any label. In LFIB, they will be having routes with labels. Okay, this is clear. So now let's assume R1 is saying,
should it be decided on basis of CEF?
we can say yes, because in the fifth table, basically what they have the best thing, right? Let's say if I want to go to 44444, the best is E0 by 0 interface, correct? Once they will put in the LFIB, they will just add a label that is 110. That's it. Okay. LFIB, it means that has a label information and a best exit interface. It means we have in the label table, we have two remote label, but that doesn't matter, because in the routing table we can have, in the BGP table we can see we can have multiple path, right? But it will do a lookup in the routing table and will find the best path. Same way here we have multiple labels to reach a neighbor, but we know that this is the best label to reach R4. Okay. Now the next thing here, once R1, let's say now R1 want to go to R4. Okay, so R4 will check, okay, what is a remote label, that is 70. So whenever R1 will send the information to R2, in the MPLS label there will be a 70. Once R2 will receive the information, it will check, okay, I'm getting a packet with a label 70. It means I have to find that label in my local labels. So it will start checking the labels and we'll find, okay, this is a 70. Now to which label I have to exchange? If I will receive 70 and this is a local label, and what is the remote label for that one? That is 1110. So whenever R2 will send the information, that packet will contain 110, we'll send it to R3. Again, R3, whenever a router will receive a packet with a label, it will start finding that label into the local label. So it will find, okay, 110, that is for 4444, and what is the remote best label? That is 150. So R3 will send the packet with label 150. R4 will receive and will check, okay, the local label is 150 and that is my own interface address, so I have to get the packet. That's it. So like this, whenever a router will receive a packet, a data packet with a label, the device will start checking the label in the local label list. Okay, once they find a local label to a route, bind to a route, it will find the remote label and will send the packet out to a new label. Again, R3 will find that label in the local table and will find a remote label, will send it to another router. So like this, the routers will keep doing the lookup. Okay. So this is a process where the devices will share the information, will generate local labels, will generate remote labels, and will find the data plane using those labels. So any doubt in this one till this point?
Fine.
No, sir, no doubt.
Okay, now the same diagram I'll be using: R1, R2, R3, R4. So one rule we have basically for directly connected routes, router never generate any label, or we can say they generate a label that is null label. Okay, so 1.1.1.1 here we have. So now this is the real thing. 2.2.2.2.2, 3.3.3.3, and 4.4.4.4. Okay, earlier we have discussed the example just to get the understanding of the labels. Okay, so one is the local route, one is a directly connected route of R1, 2 is a route of R2, 3 is a route of R3, 4 is a route of R4. Okay, so R1 will originate a null label. Okay, so it will originate a null label. But for this one, yes, it will originate a label. It will start from 16, 17, 18. Okay. R2 will do the same task. It will say, okay, 1.1.1.1, I will specify 16, but 2 is my own route. That is my directly connected interface. So I will specify null. For 3, yes, I can create 17, I can create 18. Same R3 will do, okay, for 1.1.1.1, I will be having 16, 17 for 2, but 3 is my local label, local route, right? So I will create a null, and then for this one, I will create 18. Same R4 will do 16, 17, 18, and then finally null for the local route. Okay, now they will, so as I told you, first of all, the first step, they will create a local labels. Fine. Now we have the local labels. Now these routers will exchange these labels to the neighbors. So let's say all these routers are neighbors now. Okay. R1 will say to R2, remote label is null, remote label is 16, remote label is 17, remote label is 19. For a single route, we can have same remote label, same local label. That doesn't matter. Okay. R3 will say the remote label is 16, the remote label is 17, the remote label is null, the remote label is 18. Same R2 will say to R3, 16, use null, 17, 18. R4 will say 16, 17, 18, and null. Same R3 will say to R4, 16, 17, null, and 18, like this. Okay. Null, it means whenever I will forward the packet out to a router that has a null label, it means I will remove all the labels. Okay, I'll explain the reason why. So now let's say R1 want to communicate to R4. So it will put a label. Okay, so R2 will say 16, null, 17, 18. So R1 will check, okay, 18 is a remote label. It means I have to use 18 label to reach 4444. So the R1 will send the packet out with label 18. R2 will receive, and now R2 will find, okay, I have local label 16, null, 17, 18, fine. 18, 18. So here we have that local label, and what is the best remote label? It will find, okay, for this one, next stop is R1. For this one, next stop is R3, right? And who is the next stop? The best next stop, that is R3. So I have to use 18, cool. It will replace 18 with 18 again. 18, 18. Okay. R3 will receive and will check the label in the local label table. These are the local labels. It will find 18. Cool. One remote label, that is via R2. One remote label, that is via R4. And which one is the best next stop? That is R4, right? It will check, okay, that is a null. It means now what I have to do, I have to remove the labels and have to send a clean packet. Earlier it was with layer 2, upper layer 3. Layer 3, layer 2. Now it will send the packet out to R4 without any label, null label. It means now I cannot use any label. It means layer 2 and layer 3. And R4 will receive the packet, null label. It will just receive the packet, will check the routing table, will absorb the information. So like this, the devices in the real scenario, they will work. They will create some labels. They will put some labels. They will use some remote labels to send the packet out. Routers will receive the packet. The data packet will check the local label to which it has associated and will find the new remote label and will send it to another routers. So this is how the routers exchange the information in the label packet. So any doubt till this point?
So how like R2 will identify it is received via R1 or R3?
Okay,
like
because
the label is same. So.
Yeah, whenever R2 will get a packet on interface, this one, it will get to know, okay, I'm getting a packet on this interface, and who is connected there? R1 is my neighbor that is connected on this interface, right?
Okay, so that information will also be with this packet.
Yes. Yeah, basically R2 is getting information from R1. So automatically it will get to know R1 is my neighbor and I'm getting a packet from R1, and the label I have received that is 18, I have received from R3 that is 18, right? So it will check the routing, it will check the look, it will do a lookup for the best label and will use the same label. That's it. Okay.
Yeah, so like actually I mean like it will be having some more information apart from this label as well, like this interface and all.
Yeah, it will be having another information. I will show you the information. I will show you the next store feature. Okay, I will show you the best route. I will show you the labels. The other things I'll show you. We have some commands to check those things. Okay. So once we start the practical, I'll show you how these devices will create these labels. I will show you the binding. I will show you the remote label, local label, the best label I'll show you. Okay. So any doubt to this point?
Fine.
Thanks.
Okay. One more thing here. Let's say this was connected to a customer as device. So this will receive a clean packet. Okay. We'll check. Okay. That is reachable by labels. So it will add a new label. So it means R1 is injecting a label. R3 is removing a label. R2 is like swapping the label, right? Now, so we have three kinds of router here. LSR. What is LSR? Label switch router. Okay. So one we have that is ingress LSR. Ingress LSR. One we have that is intermediate LSR. Okay, one we have egress LSR. Okay, so about the ingress, receive a known MPLS packet. So if I talk about ingress LSR that receive a known MPLS packet, if I'll talk about intermediate LSR, receive a MPLS labeled packet. Egress LSR, it will again receive a MPLS labeled packet. Okay, so the first understanding for this one, ingress, it means it will receive a known MPLS packet. Intermediate, it will receive a label packet. Egress, it will receive a label packet. Guys, any doubt?
No.
No.
So ingress LSR, it will receive a known MPLS packet. Okay, it means that does not have any label. Intermediate, it means yes, that has a label. Egress, that has a label. Okay, now one interface should not be MPLS enabled. One interface, at least one interface should be MPLS enabled. So if you see these conditions on a router, so yes, that is ingress LSR. Okay, intermediate, all the interfaces should be the part of MPLS. Same here, at least one interface should be the part of MPLS, and one interface should not be part of MPLS. Okay. What this device will do, the ingress LSR will receive a unlabeled packet and will add a new label, or sometimes we say here for the ingress, that is push. Okay, it means it will add a new label to data. For the intermediate, it will just swap a label. It means it will get a labeled packet and will remove it and will add a new label again. Okay. Finally, egress LSR. What this will do, it will get a packet with label information and it will remove label and will send a clean packet to other router. It means what we have here, we have three types of router: ingress LSR, intermediate LSR, and egress LSR. Okay, what is ingress? That will push the label, that will add a label to the route. Intermediate, that will swap the label, that will exchange the label. Okay, and egress LSR, that will pop the label. Okay, swapping, receive a packet with a label, it will replace with a new one. Egress, it will remove the label, it means it will send a clean packet to the neighbor, and this is called your PHP. Okay, this is called your pan ultimate hop popping. Okay, so just tell me, any doubt till this point?
No, sir.
Say push, swap, and pop. This whole process is known as PHP. Yeah, only
No,
pop the level.
only this pop, the egress LSR. So once a egress LSR will do this pop, that mechanism is called as PHP. It means before one hop, the device will do a pop of the label. Okay, it means what happens in the background. So in this condition, if I talk about 4444, R1 is getting an unlabeled packet from a C router. So R1 will act as ingress LSR. Okay, that will add a new label. R2 will act as intermediate LSR, that will swap the label. And once R3 will receive the label, will receive the packet, it will check, okay, now I have to remove the label before one hop. Till this point, we have MPLS domain, but before one hop, R3 will pop the label. So before one hop, we are popping a label. That process is called as PHP, pan ultimate hop popping. Okay. Before one hop, we are removing a label.
Okay,
that
sir.
process is called as PHP. Okay.
Sir, suppose we have a system connected at R4. So in that scenario, POPs happen at R4 or R3?
R3. Because, okay, we have to check the MPLS score. If the MPLS score starts from R1 to R3, it means R2 will do the PHP. If the MPLS domain ends on R4, it means R3 will do the PHP. Okay. The one hop I'm talking about, MPLS hop. Okay. Before one hop, the device is removing a label. It means before the MPLS hop. Okay. Not the real destination. Clear?
Okay,
So, any other doubt, guys? Anyone, any doubt till this point?
For me, no.
Okay. So I'll just take a new example. So let's say we have R1. Okay. We have R2. We have R3. And we have R4. Okay. In between we have R5. And R4 is having a route that is 44444. Okay. Even R2 will be having 4444, right? R5 will be having a 44 route in the table. R3 will be having a route in the routing table that is 444. Even R1 will be having that route in the routing table, right? But right now, if I just talk about the routing table, that will be having a best path that is via R5, correct? If R1 want to communicate to R4 in the normal table, in the normal IP packet, using the normal IP packet, that will use router R5 to reach R4, correct? But once we talk about the MPLS, what happens in this condition, R4, let's say R2, R3, R5, R4 will create some local label. So right now we'll just talk about the label, the packet 4444 and a label. So let's say R2 will originate a label that is 10, R3 will originate that is 20, R4 will originate, okay, that is my route, that is null. It will originate 30, let's say, and R1 will originate 40. Cool, no problem. So these are the local labels. Okay, now R1 will exchange the label to R1. So take 10 as remote label. R5 will say take 30 as a remote label. Same here, R3 will say take 20 as remote label. R1 will say take 40 as remote label. Same here, 10 as a remote label, null as a remote label. Same here, 40 is a remote label and null as a remote label, correct? Via R4. So any doubt in this condition, in this diagram?
No.
Now, whenever R1 want to communicate to R4, right now it has two labels, 10 and 30, correct? We have two best path. Sorry, not best path, two path. Okay. So the device will check, okay, in the LFIP table, it will be having this next stop that is R5, this as a R2, and yes, this is the best next stop. So whenever the device R1 want to communicate to R4, it will send a packet out to R5 with the label 30. It will check, okay, that is 30 and what is the best, that is null. It means it will route the packet out, a clean packet, a normal IP packet to R4. Okay, once R5 goes down, what happens in the background, R1 will detect, okay, my neighborship, my MPLS LDP neighborship is down. Now what I have to do, whatever labels I have received from R5, I have to mark as down. R1 will remove those labels from the table and will just keep it one single label, and then it will route the packet out to via this way. So if my MPLS core broken, right, if let's say R5 goes down, what will happen here? Even your MPLS will break the neighborship, will remove all the labels via that neighbor, and will be using the other label. It means again, this is just a normal routing, right? If I talk about a routing table, the normal IP packet will forward like this, right? If we have best path via R5, that will go via R5, and if that goes down, the R1 will shift the traffic via R2. Same in the labels, what they are doing, they are using some labels 10 and 30. That is via R5, that is via R2. If R5 is working fine, we will go via R5. When R5 goes down, even I will remove the labels, and now I will go via R10. Using label 10, right? So MPLS basically, that is just a we can say that is just an application, okay, that is running over the protocols. Okay. Now,
so in this case, how it is identifying that the route from the R5 is best? I mean, how R1 is able to know this?
In the background, they have the protocols. Let's say we are using here OSPF. In the OSPF, using OSPF, R1 will get to know R2 is the second best, R5 is the best, correct? So once they will create some labels, let's say we have route 44444. Once they will try to originate labels, so that will originate for this one 10, that will receive 10 10 and that will receive 20. That will also check this thing once the device will put those things in the LFIB. Okay, this is not the best router. This is the best router, so I have to put this label in my LFIB. Okay.
Okay, got it. And for this is an example for one route, and we will be having a multiple routes in our production environment. So like for each and every route, this like I will say like LSP. So it is defined on the basis of this hope and hope basis, right? Only.
Yeah.
Is it correct?
Yeah. Correct. Absolutely. If let's say we have 1 lakh route, the same process will happen for those 1 lakh route, and we'll be having a different LSR, different ingress, different egress, different swapping router for each route. Okay. Sometimes R1 want to communicate to R3, sometimes it will communicate to R4, to R2, to R5, right? So in every case, the LSR routers will be different for each route. Okay.
Okay.
Look, in this
so
case,
yeah. So to start this path, it will start from the it will start in a reverse manner, right? Like the destination is that 4.4.4.4.4. So first of all, it will propagate it to the R3 in this manner, or from the source it will be starting.
Okay, no, basically that's up to the control plane. Okay, so initially they will exchange the control plane, right? Same in the MPLS, they will exchange the labels. That labels will act as a control plane. R4 will advertise a label to this one, to this one. Even now, R3 will advertise a local label to R2. This will advertise a local label to this one. R2 will advertise a local label to R1. The same way that the routers exchange the control plane. Okay. If R4 will send a control plane, a label to R3, then only R3 will be able to add a label towards R4, right? Same for R3. Whenever R3 will send a label to R2, let's say to reach 444, use a label 20, then only R2 will be able to send a real traffic towards R3, correct? So that's the same mechanism that we have in the case of normal control plane, okay?
Okay, for an example, in the same diagram, if I am having a same network 4.4.4.4 after this R3, so like how in that case this
again, they will check the routing table. Which route is the real best route for me? If they find the other path as a best path, so they will send the packet out towards that way. Okay.
Like in this example, R3, like for that 4.4.4.4, for R3, the best path will be via R3, and for R4, it will be via R4. So they both will be sending their label with that with this destination to their neighbor, and in a similar way, R1 will be getting the different label like from R2 and R5, but the destination will be different. So
yes, in this case,
how it will segregate like?
Okay, let me explain you one situation. Okay, so let's say we have R1. That is connected to R2, R3. So let's assume we have these routers, okay, and here we have R4, and here we have R5, okay, and they are connected like this. Okay, and where I have configured MPLS on this interface, 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 on this interface. Okay, and what is my LSP right now? Label switch path, that is via R2 only. If these routers will route the packet via R2 only, in that condition only, we will be having a successful communication. Okay, now we are running OSPF in this core network. So R4, R1, R2, R3, R5, these are the part of OSPF also. So whenever R4, okay, and let's talk about the loopback 55555. Okay, so this is a route, this is a route, this is a route, this is a route. Okay, so R3, R5 will say, let's say this will create a local label that is null. Okay, R3 will create a local label that is, let's say 10. R2 will create that is label 20, R1 will create that label is 30, this will create a 40. Okay, now I will take remote label, null, that is 10, that is 20, and that is 30. So I'm just taking one single, that is best label. Okay, so in this case, what will happen here? R4 will check, okay, 30 is the best label. And what is the best path to reach that router? That is this path. Okay, cool. R1 will receive the information. 30. Now I have to swap with 20. But now it will check to reach 55555. What best path I have in the routing table? What is the real next hop? That is this interface. So what will happen here in this case? R1 will send the traffic out to R3. The device will not check, okay, I'm getting a label 20 via R2. No. This will check, okay, the best path to reach 555, that is via this router. And I have to use a label that is 20 because for me, the remote label is 20 to reach 555, but the next hop is best via OSPF, via directly this link, right? So R3 will receive the information, it will check, oh, this is unlabeled interface. Okay, but I'm getting a labeled packet. So now I cannot understand the label. I have to drop this packet. So in this condition, what will happen here? The communication will not happen if we have a diagram such like this. Okay. Now your questions. Guys, any questions?
No.
I hope your question is clear now.
Yes.
So if routers choose a different path and that path is not labeled, right? So definitely the communication will not be successful. Okay. In that case, what we have to do just to make the communication reachable, we have to increase the path cost, or we have to enable MPLS here also. Okay. Because R1 is having information like to reach 555, I have to use a label. Okay. Any questions?
No.
Okay. Now let's move to the header. So the header size is 4 byte. Okay. So that will be always in between. First we'll be having a layer 2. Okay. Then it will be having a MPLS header. Okay. So then they will be having MPLS header, and finally they will be having IP header here. So whenever the routers put a MPLS header, right, the labels, so that label will be inside in this MPLS header. Okay. So this header will always be in between 2 and 3. So this is my layer 2 information, right? And this is my layer 3 information. So this will always be a 2.5, layer 2.5 header. Okay. Now this header, size of this header will be 4 bytes. Okay. 4 bytes, it means how many bits we have here? 32 bits. Okay. So if I'll start from starting, the first 20 bits. The first 20 bits are reserved for the label value. Okay. Now the next 3 bits are reserved for the experimental purpose. Okay. The next one single bit is reserved for S. What is S? This is your bottom of stack. I'll explain what is bottom of stack. Finally, how many bits we are remaining? That is 8 bits. Okay. So these are for your TTL. So like in IP header, we have TTL, same thing here we have in the MPLS header. Okay. Now, so these labels, as I told you, the size will be 20 bits, right? So they will start from 0, 1, 2, 3, 4, 5, right? So that will go to up to 20 bits, right? So starting from 0 to 15, these are reserved. So whenever the routers will start originating local labels, they will always start from 16. That's why they will start from 16, because 0 to 15 are reserved. Okay, they will start from 16. So these are for the labels only. Then 3 bits are for the experimental purpose. So just leave it right now. Okay, that we can discuss in the cooperative services. Then we have S, one single bit. So one single bit can be 0, can be 1, right? So that is saying bottom of stack. If that is 1, yes. If that is 0, no, right? So now again, what is the bottom of stack? So let's say we have an IP header, we have an MPLS packet with a IP header and MPLS header. Okay, IP, MPLS, and layer 2. So if we have a normal MPLS mechanism or a normal MPLS core, so this will be the packet. Okay. If we have a VPN v4 neighborship and those kind of neighborship, MPLSL3VPN, in that case, how this will be look like? IP header, MPLS header, MPLS header, dual MPLS header will be having here, and then L2. Okay, so in this case, the device will say, yes, this is the bottom of stack. It means, yes, this is the last label that we have. But now, this MPLS header will be having this bit as 0. This MPLS header will be having that bit as 1. It means this will say, no, after me, yes, we can have one more label. If that is 0, again, it will say, yes, after me, I can have one more MPLS header. But that is 1 right now. So this will say, okay, above, I can have one more label. Once the devices will check this label, okay, if that is 1, yes, that is the last label. Okay. So using bottom of stack, if that is 1, that is saying, yes, I am the last label. If that is 0, that is saying I'm not the last label. Above me, we can have more MPLS header. Okay. Finally, the TTL value. That is 8-bit. It means that can start from 0 to 255, right? So if a packet goes to 0, that will be discarded and will start from 255. So it will start from 255 or any other number that we'll discuss later. Okay. So that has just a mechanism of TTL. The size is 8-bit as we have in the IP header. That's it. So this is an MPLS header. Just tell me if you have any doubt in this MPLS header, you can ask.
Is it possible, like for this TTL value, for an example, we have more than 255 router? This is a situation I'm telling you may not be possible.
No. The packet will be dropped in that condition.
Okay. So the core cannot be having the router more than 255.
Yep, never. They can have, okay. So those things we'll discuss later, how they can have, okay.
Okay.
If I talk about a normal MPLS core, yes, they cannot have. But if we have more than those MPLS, so yes, we can have. I'll explain these things later. Sorry? Santosh, any question? Okay.
No, sir, no, sir. By default, it was unmute.
Okay, no worries. Okay, so this is about the MPLS header and labels. Okay, let's take a break of 15 minutes. Okay, and then we will start label distribution process, how the devices use a protocol LDP, how they exchange the labels. These things will start. Okay, so we'll start at 11:45. Okay.
Okay.
We'll start by 11, right?
11:45.
11. Okay.
This is 11:30. So now I'll start at 11:45. Okay. Label distributing process. So basically we have two protocols to distribute the labels. Okay. Now the first one is TDP. The second one is LDP. Okay. What is TDP? Your tag distribution protocol. Okay. LDP is your label distribution protocol. Okay. So tags distribution protocol, that is your Cisco proprietary protocol. Okay, and have less features to use. But LDP is your open standard and have n numbers of feature. Okay. So we'll discuss only LDP here. Okay. The TDP, we never use TDP in any case. Okay. LDP is your layer 7 protocol that use UDP packets to exchange the information. Okay. That use a port number 646. Okay. So initially, whenever they will try to form a neighborship, they will exchange the packets on 646. Okay. This is a multicast protocol that use a protocol number 224.0.0.2. In the case of IPv4, if that is IPv6, that use FF02, that's a multicast range, ::2. Okay. We do have some hello and hold timer here. For LDP, hello are sent in every 5 seconds, and the hold timer is 15 seconds. Okay. We have multiple ways to enable LDP on an interface. Okay. The first one, that is global. Okay. Or we can say we can go to the interface level. Okay. So if I talk about the global, it means we have a single protocol. We can use OSPF to enable globally. Let's say we have 10 interfaces and those are the part of OSPF. Okay. And I want to configure MPLS for those interfaces, LDP for those interfaces. So I can use OSPF to enable in one single shot for all the interfaces. Those are the part of OSPF. Okay. And for the interfaces, if underlay like protocol is EIGRP, RIP, static routing we are using there, or we are using OSPF, any protocol we are using, we can just go to the interface. Let's say the interface is F0/0 and can say MPLS IP. Okay. In OSPF, we can run router OSPF1 and MPLS LDP auto config. If I press enter here, it will not check how many area we have. It will just enable LDP on all the interfaces that are the part of OSPF. If I will specify area, it means let's say the device has two area 0, area 1. So now the device will just enable LDP on the interfaces. Those are the part of area 0. So these commands we use in the case of iOS. Even these two commands. If I will talk about the iOS XR, right? What we done there, if I talk about OSPF, okay. So router OSPF1 address family IPv for unicast, then we run area 0, okay, and then we can configure MPLS LDP autoconfig. Okay, so this is just a syntax. Okay, once we'll start the practical, we'll show you the real commands. Okay, these are the real commands, but these are the syntax. Okay, MPLS LDP autoconfig. So these commands we can use in the iOS XR to enable in the OSPF basis. Okay, on the interface level, how we configure on the interface level, we just go to the MPLS LDP. Okay, we go to the address assembly IPv4 and we just enable interface. If let's say that is the gig 0x0x1 interface, gig 0x0x2. So how many interfaces we have, we can just enable like this. Okay, so these commands we use in the case of iOS XR. I'll do both. I'll show you how we can run these one, how we can use the iOS XR commands also. Okay. In the background, as I told you, like whenever they will create some neighborship, they will exchange some packets, right? So they will exchange a hello packet as we exchange in other protocols. So this is a multicast protocol. So if I talk about EIGRP, OSPF, in those conditions also, those are multicast protocol, and they exchange the hello packet also. Same here, we have hello packet. Okay. Now about this hello packet, hello messages are sent to all routers that are reachable through that interface, because here again, let's say if I talk about OSPF, they form the direct neighborship. Same here, they form the direct neighborship. So whatever interface we have enabled, on which interface we have enabled, they will start sending packets on that interface. Okay, hello messages. Hello messages are, they use well-known port, that is 646, and this is your UDP port. Okay, so hello message hello message use well-known UDP port, that is 646 always. Okay, now one more thing they will add in the hello packet, they will add a 6-byte LDP identifier. Okay, so now they will add this TLV. Basically, this will be in the TLV. I will show you what will be in the TLV. So once I will open the packet, I will show you the LDP identifier. Okay, all the routers will create a router ID basically, and highest loopback address will be using as a router ID. Okay. In the case of MPLS, let's say if I talk about OSPF, I need to configure, if let's say I want to use a loopback address, right? So I have to configure OSPF on that interface also. But if I talk about MPLS LDP, we just need to configure MPLS LDP on the physical interfaces, not on the virtual interfaces. Okay. Reason, MPLS LDP we are using just to form a neighborship with the directly connected neighbors. Okay. Let's say we have R1 here, we have R2, and we have R3, and they have the loopback addresses also. Now if we comes to the configuration part, right, we just enable MPLS on this interface, on this interface, on this interface, on this interface. We never enable MPLS on the loopback addresses, never. Okay, once they will be having those links available online, right, they will form a neighborship, and once they will be having neighborship, then they will check what routing table we have, and according to that they will originate labels and will exchange it to another label. It means whenever you run a protocol MPLS, just need to check the physical interfaces. That should be enabled on the physical interfaces only. Okay.
Neeraj, why do we not like form the neighborship with loopback address?
With loopback address, okay, we can say because they are using a router ID as loopback address. So if we are using MPLS LDP, so those loopback addresses should be reachable via IGP. Like if let's say we are using OSPF, right? So those loopback addresses they are using for a router ID, those should be reachable from each other. Okay. Yeah. So as I told you, they will be using a higher loopback address always. Okay. So this is the hello content, and the other things I'll show in the packet. And one more thing
is actually one question. In the beginning, like you said, I mean, is there any specific protocol we are needed to enable the MPLS? Like in the beginning, I think you asked for the EIGRP. So can you please explain about that?
Sure. So basically, to enable MPLS, that doesn't matter any protocol you can use. Okay. If it comes to global configuration, okay, let's say we have configured RIP protocol, we have configured EIGRP, or we have configured static routing to make the communication only. So if we have these protocols and want to enable MPLS, then specifically we have to go to the interface level. Okay. But if we have OSPF, so we can use OSPF to configure MPLS, or we can go to the interface level also. Okay. So if we have EIGRP and RIP protocol, so globally we cannot configure MPLS. We have to go to the interface level and have to run the command MPLS IP. Okay.
Okay.
One more thing, they will exchange in the hello packet. They will share the hold time in the hello packet. So the default is 15 seconds. Okay. So any doubt till this point?
No, as of now there is no doubt.
Okay. So initially, once they will exchange the hello packets, those hello packets basically they will be UDP hello packets, right? Once they will exchange the hello packet, they find okay, we have this neighbor, then they will initiate LDP session negotiation. Okay. So at that time, what they do, they use TCP session. If I talk about BGP, even in BGP, before neighborship, they exchange some TCP packets, right? They configure a TCP session. If the TCP session is successful, right, then they will move to the BGP process, right? Same here. First of all, they will exchange UDP hello packets just to identify the neighbors, just to discover the neighbors. If they discover the neighbors, they will try to create a TCP session with them. A TCP session, once that is successful, then they will initiate those label process, those label exchange process. Okay. This is clear.
So it means the first of hello packet will go via UDP message.
Yes.
Like the protocol will use by UDP, and if the neighbor is discovered, then we'll proceed with the TCP connection.
TCP, right? And finally, once the TCP session is up, they will exchange some information. The keep alive timer, they will exchange the method what they are using, LDP or that is TDP, whatever information they have, they will exchange these things. And finally, once the neighborship is up, like in BGP, they will start exchanging keep alive messages. Okay.
Okay. So Neeraj, as you had discussed the OSPF LSA 6 in OSPF, right? So will we use that LSA in somewhere in MPLS? What we are discussing today?
No, nothing.
Okay.
Any other doubt?
No, for me.
Okay.
Actually, that
so right now, as I told you, basically whenever they will exchange the information, they will exchange to directly connected neighbors. But in this protocol, what they can do one more task. They can configure a neighborship with indirectly connected neighbors. So if I just take an example of OSPF, in OSPF, we can just form a neighborship to directly connect neighbors. By default in LDP also, we can have a neighborship only with directly connected neighbors. But let's say if I want to configure a indirect neighborship, so yes, we can configure using some special commands. Okay. So now I'll show the commands, but I'm not running the commands right now. I'll just show the commands. Okay. those indirectly neighbors are basically we call that as targeted neighbor, or we can say we use targeted hello packets. It means that packet will directly go to the specific address. If I'll talk about, they will search a neighbor, they will discover a neighbor, that will be a multicast. But if I'll say a targeted hello, it means in that case the packet will be unicast. The device will send a unicast packet to the neighbor. If that find a neighbor, yes, they will form the neighborship. And in the case of targeted hello, they will not send the packets in every 5 and 15. They will send the packets in every 60 seconds, and the dead will be 180 seconds. So if we have directly connected neighbors, the 5 and 15 will be there. If we have targeted neighbor, that will be 60 and 180 seconds. So on both iOS and iOS XR, the commands will be different. Okay. And the concept will be same, only the commands will be having some different parameters, some different way to configure it. Okay. The context will be different at that time. So just tell me, any doubt till this point?
No, till now there is no doubt.
Everything is clear?
One thing actually, Neeraj, I want to know.
Your voice is a bit low. Hello?
Hello?
Yeah, now it's clear. Yeah.
Yeah. Hello? Now it's
Yeah.
clear, right? Yeah, actually one doubt for me, that router ID concept is there, no, in MPLS.
Yes.
That router ID exchange in that UDP hello or that in TCP?
Okay, so basically, as I told you, initially they will exchange a hello packet, correct? That is a UDP based packet, correct?
UDP based, yeah.
So in that UDP packet, they will say that this is my router ID. So yes, the packet will be UDP, and in that packet, they will exchange that router ID. Okay.
Okay, it means that, okay, UDP. Okay.
Yeah. This is clear.
Yeah, clear.
Okay. Now we'll discuss one more thing here. As I told you, I'll take an example. Let's say we have R1, we have R2, we have R3, we have R4. So in this case, once we enable MPLS on these routers, right, what they will do basically, they will start exchanging labels, right? So once the neighborship is up, so the first process, they will bring the neighborship up, right? And once the neighborship is up, second task, they will automatically exchange labels for all the routes. That is true, correct? But now we have two concepts here. The first concept is unsolicited downstream. Okay, the one we have downstream on demand. Okay, so we have two things here, unsolicited, solicited, downstream, and one we have downstream on demand. Now what is the behavior and what are the difference in between these two things? This is default one. Okay, it means whenever routers form the neighborship, automatically they generate labels for all the routes, definitely. But right now I don't want to generate labels for all the routes. Then what we can do, we can enable downstream on demand. Okay, so in this one, what happens in the background, the MPLS architecture allows an link state router to request for a specific route or to a bunch of routes, we can say, or we can say this is being done by ACL. Okay, so unsolicited downstream, yes, by default they will exchange the labels, they will generate labels for all the routes. That doesn't matter how many routes we have, they will just start creating labels for all the routes and will exchange to the neighbor. But in downstream on demand, what we have to do in that condition, basically the router itself, the LSR router itself will request to a specific route using us ACL. So in ACL, if we have 10 routes, it means routers will ask, just provide me the label. for these 10 routes. If in ACL we have one single route, so the device will just ask, okay, just provide me one single label. And how this works again, routers check route in routing table and find next hop to send a request. So before sending a request to a neighbor, right? So let's say I just want to get labels for a route that is 1.1.1.1.1. Now, before asking this information, what I will do here, I will just do one thing. I will check my routing table to reach this neighbor, to reach this route, which neighbor is present there, which neighbor is there in my table, right? It will find, okay, 12.0.0.1 is the router, is the next hop that I can ask. That is the best next hop. So the router will check the routing table to find the next hop as to send a request. So once it finds, it will send a request. Please provide me a label for this route 1.1.1.1. Okay. So this mechanism is called as downstream on-demand label. Okay. Label distribution process. So if that is unsolidated, let's say we have 3 routers, R1, R2, R3, right? And they have 1.1.1.1, 1.1.1.2 to 1.1.1.3, right? We are using here unsolidated downstream, right? So what they will do, actively they will share 10 is the label for 1.1.1.1.1, 20 is the label for 1.1.1.2, 30 is the label for 1.1.1.3. Same R2 will share, same R3 will share to the routers. But if we have downstream on demand, we have these routers R1, R2, R3. We have 1.1.1.1 here, we have 1.1.1.2 here, we have 1.1.1.3. They will be having the same database. It means they will be having 1.1.1 also. Now R2 will just want to get a label for 1.1.1.1.1. So R2 can request that 1.1.1.1 is best reachable via you. Please provide me the label. It will ask for the label and R1 will send a reply. Okay, this is a label number 10 to reach 1.1.1.1. Please use this label to reach 1.1.1.1. Okay, but in this condition, both routers should be negotiate this thing. If downstream on demand is enabled on this interface, then that is mandate that should be enabled on this interface also. It means using these interfaces, they will never negotiate anything automatically. They will just wait for the indication. Once I will put a ACL here, they will start requesting to each other and they will exchange the real information. So this is your types of distribution, unsolidated, and one is downstream on demand.
Neeraj, seems your voice is breaking. Is it only for me or for everyone?
Hello?
I am getting like it's no problem.
Yeah.
So any doubt in this one, unsolidated and downstream on demand? So basically these two are the distribution method. Okay, by default what we use unsolidated. Okay, this is a default one. And if you want to enable downstream on demand, so yes, we can enable by using some specific commands. So I'll show you that in the iOS XR only. So basically that is a feature of iOS XR only. Okay. So any doubt till this point? Any doubt if you have?
No.
All clear till this point?
Yeah.
One more thing here we can control. In MPLS, let's say we have a by default that is unsolicited downstream, right? So by default that will originate labels for all the routes. We can guide my router. You can originate labels only for the routes that has a /32 mask. It means for the loopback addresses. Because let's say we have R1, we have R2, we have R3, and we have R4. So this R4 will be having loopback of 1, loopback of 2, loopback of 3, and the segment address of 12, the segment address of 23, right? So R3 will be having that information that 1 is on /32, 2 is on /32, 3 is on /32, but 12 is on /8, 23 is on /8, and this 34 is on /8. So once I will say allocate label for host route only. So we run a command, a special command, allocate labels host route. Okay, so this we enable basically this command. Once we enable this command, what happens in the background? R4 will just originate labels only for the routes those are on /32 mask. Okay, and they will never generate labels for a transit interface. So these are called as transit interface. So they will never generate any labels for these transit interface once you enable this command. So yes, we can control the label distribution process using these commands. Okay. So it means now we have both ways. One, if you want to set it automatically, yes, you can set again in automatic. You can put these commands to enable to do some filtering for the labels. It means just originate labels for the loopback addresses. Do not originate labels for the transit interfaces. Okay, and if you want to just do a request, so you can just enable downstream on demand to do to send a request for a specific route, right? So any doubt till this point?
No, no doubt.
Okay, so now I'll just open the topology. So first I'll explain how we can use this diagram and what are the features that here we have. Okay. So this will be my MPLS core. This will be MPLS core. Okay. And in this MPLS core, just to make the communication possible, I'll be using OSPF. And we have here, this is my iOS XR device. iOS XR device. Okay. And these are my iOS devices. So it means I can enable MPLS on iOS XR and on iOS device. It means you'll be having idea how we run MPLS on normal routers, how we run MPLS on the iOS XR devices. Okay. Then I'll enable BGP here. So just for the communication, just to exchange the routes, we'll be creating an IBGP session in between these two routers. Okay, using BGP AS number 100. And then this was about the MPLS core. Now the customers, the customer A here we have, the customer A here we have, these are the same sites, same here customer B, customer B. So finally what we need here, whenever this user will try to communicate to an address 68, 68, 68, 68, that should come to only this router. And whenever this router wants to communicate to this device, that should come to only this device, not to this one. Okay. So to make this communication possible, what we will be using here, we will be using, so as you can see, we are using a single interface, right, to connect multiple customers, or we can say this is our shared approach, right? As I told you, we have peer-to-peer with shared approach, right? So we are using here shared approach. What I'll be doing here, we have this single interface that is gig 0 by 0 by 0 by 6. Now, I will break this interface into two sub interfaces. Okay, 6.4 and 6.5. What I'll do here, I will put this interface into another VRF. I will put this interface into another VRF. So whenever I will receive anything on this interface, that will be in the separate table. And whenever I will receive anything on this interface, that will be in the separate table. And I will allow here a VLAN 4. I will allow a VLAN 5 here. So it means whenever the device will send the traffic out to this interface, that will be having VLAN 4 tag, and same here that will be having VLAN 5 tag. And this interface I have configured as trunk. I will configure this port as trunk. This interface that is connected to customer A, that will be in the VLAN 4. This interface that is connected to R6, that will be in the VLAN 5. So whenever this device will send information the switch will receive in the VLAN 4 and will forward using trunk port with the tag VLAN 4, and this interface, basically the physical will receive the packet, it will check what VLAN we have, that is VLAN 4. It will hand over to this one, it means that will hand over to a different VRF. Same, whenever R6 will send an information, switch 1 will receive in the VLAN 5, it will hand over to trunk port, and 0/0/6 will receive with the VLAN 5, it will check, okay, this is 4.5, I will hand over the information to this one, it means that will be in the separate table, a separate routing table. Same in this condition, and finally, once they will be having routes here, I will be using here VPN, V4 neighborship to exchange the routes. And one more thing here, as you can see in this diagram, we are using all the protocols. So we have BGP here, we have OSPF here, we have RIP here, we have EIGRP. So in this diagram, I will show you how we can run OSPF, EIGRP, RIP and BGP on iOS XR, how we can enable these protocols on the iOS XR, and then I will show you, because the device will get route from OSPF and want to send to BGP. So we'll be having here redistribution also, a mutual distribution, right? Because this is OSPF. So I have used OSPF, EIGRP and RIP reason just to show you how we can do a redistribution on the edge routers on the iOS XR devices, and how we can do a redistribution into BGP. That's a bit different task here. Okay, and that's it. Because if I just use BGP everywhere, it means there will be no use of redistribution. You will never get to know if we have a neighbor that is in OSPF only, how we can get the routes and how we can send the routes to that neighbor. Okay, so we have all the protocols here in this topology. I'll show you everything. Okay, so just check the diagram and tell me if you have any doubt in this diagram or anything is missing here. Just tell me.
Sir, why we are using switch here?
Switch, okay. So basically, I just want to use here an approach that is shared approach. Okay, so in that case, we have to use a switch. Okay, in shared approach, basically what we do, we will be having a single P, we'll be having multiple customer edge, and we'll be having a single interface of P. So if we have multiple interfaces, multiple customer and single P interface, we have to use a segment that can have multiple customers, right?
Okay.
Yes.
Any other doubt? So let's start the practical. Okay. Let's start devices. So in this diagram, IP addressing is already done. Okay, we just need to enable the protocols and the shared network approach. I will start showing you from switch. So on switch, the port number 4 is a part of VLAN 4, cool. The port number 5 is a part of VLAN 5, and the port number 1, you can see here the port number 1 is our .1 queue. Okay, that is a trunk port. Same here for the switch number 2, we can see port number 4 is having VLAN 4, port number 5 is having VLAN 5, okay, and the port number 1 is our .1 queue trunk port, that is not access port. Okay, and on port number 4 we have this user. Same here on port number 4 we have this user, port number 5 we have this user, on port number 5 we have this user. Now next thing, We have some interfaces here. I will show you. I will configure these things. Okay. It will just take some time. Just wait.
Like in this case of the switch, you shows that the trunk port 1 is .1Q. So, but why that is in VLAN 7 only?
Okay, basically whenever we configure trunk port, there will be a native VLAN, correct? So that is showing that is just a native VLAN.
Yes, yes.
Okay.
Okay, okay. So 7 is a native VLAN. Okay, fine.
Any other doubt in this one you can ask.
Keep any VLAN apart. Like we can keep any VLAN apart from this 7, right?
We can use any VLAN. That's a random with 4 and 5. No, not specific VLAN.
Okay, so can we use 4 or 5, or we cannot because they are already part of access?
No, we
right.
can use.
So we cannot use them, right?
Any number we can use here. Any number. Okay. Whatever VLAN I will be using here, so that we have to use on the sub interfaces also. Okay.
Okay, okay.
You can see in the status, we can see the port number 1 is in .1Q mode with native VLAN 7, right? And the port number 4 and 5 is in the access mode with VLAN ID 4 and 5. Okay.
Yes.
So what will be the steps to configure these things? First of all, I will enable sub interfaces. Okay. After sub interfaces, I will configure VRF. After VRF, I will configure IP addresses on those interfaces. Okay. So once I will configure these things, it means on the P, I'll be having the configuration. After that, I will configure OSPF in core, in ISP core. Then over OSPF, I will enable BGP. Okay. So once I will be having BGP, I will do everything using BGP and will run OSPF, BGP, and RIP and EIGRP with the CE devices. Okay, we'll do the redistribution. We'll do the redistribution and one more thing. Yeah, finally we will enable MPLS just to check the data plane forwarding. So before MPLS, I will show you the control plane will be propagated end to end, but not data plane will be having some issues in the data plane. And then I will enable MPLS to propagate the data plane. Okay. And one more thing here. Once we talk about the VRF, so let's discuss something about VRF. So if we talk about two things, one we have VRF and sometimes we listen that is VRF Lite. VRF light, it means that is without RD, without RT import export values. But if I talk about VRF, it means that yes, we are using RD value, we are using RT value. So if we have a scenario where we do not have any BGP configuration, we do not have any VPN v4 route, yes, in that condition we can just use VRF light without any RD, without any RT, right? But if we have BGP there, right, we want to exchange the protocols with my customer, with my provider edge, right? In that case, we have to use RD, RT values, okay? Now, so I think the difference between VRF and VRF light is clear. Now, the next. VRF. Whenever we get a route in VRF, routers will not be having power to exchange the route with other IBGP neighbor. Okay. How we can give the power? We need to enable VPN v4 address family. Okay. So in this case, we need to configure VPN v4 address family, then only the routers will be able to exchange a route that is in VRF. Reason behind, a normal IPv4 route, the size for this route will be 32-bit. Correct. Once the route comes into a VRF, so in VRF we use a RD value, route distinguisher. Okay. For the RD, the size for the RD is, any idea, guys?
64 bit.
64 bit.
64.
Yeah, correct. So once we get IPv4 route into a VRF with RD, so the combination of IPv4 plus RD, that is called as VPN v4 route. It means 32-bit plus 64-bit. The combination for this one is 96-bit. So to exchange a IPv4 route, only IPv4 route, yes, normal IBGP is enough. But to exchange a 96-bit route, what we need here, we need a VPN v4 address family. Okay. And basically this RD is a part of extended community, and by default, once we enable VPN v4 in that address family, extended community is enabled by default. So once we enable VPN v4 address family, yes, they will be able to exchange the routes. So now I'm saying they will be able to exchange the routes. But they are not exchanging right now. When they can exchange, so once we have a route in VRF, we have to export and import, right? So yes, we have VPN v4 address family in between some routers, right? But still they will not exchange the routes automatically. What I need here, I need some import export values. So that is called as route target import, route target export. So let's say we have R1 that is getting some routes into the VRF. So I have to say your export value is 100, and we have other routers. If someone will import that value, let's say R3 is importing 100 value, right? It means whatever routes I will receive in this VRF, R3 can easily receive the routes. Just for the reverse traffic, this device will export some routes, and this has to import that value that, let's say this is exporting 200. So this should import 200 just to reverse the route. Like this, we have to use import export values to exchange the real traffic, or we can say to exchange the routes between two VPN v4 neighbors. Okay. So I'll do one by one these things. Everything I'll do one by one in the practical. Okay.
So what is VRF definition?
VRF, virtual router forwarding.
No, complete definition.
complete definition. Basically, once we configure VRF, that will be having a separate routing table. Okay. So if we have separate routing table, the device will maintain those routes. Guys, I'm getting words. Can you just mute? Hello. Okay. So about the VRF, that is virtual router forwarding. So once we configure VRF, that will start maintaining another routing table and will get all the routes separate in different table. Okay, so this we use just to get a virtual router. So if you remember in switching, what we do, we use VLANs to separate to separate a physical into multiple logical switches, right? Same here, VRF we use to separate one single router, a single physical routing table into multiple routing tables, a virtual multiple routing tables. Okay.
You mean to say logical separation of the customers?
Yes.
Okay. आवाज नहीं आ रही है.
Yeah, I'm just waiting. Okay, so yeah, now we can do the task here. So let me just show you the interfaces. Do show IP interface brief. So we have these interfaces, we have sub interfaces also. So I'll just configure some addresses here, or I'll just remove first of all. We'll show you from starting. Do show IP interface brief. Okay, cool. So we have these things here, right? So first thing I'll configure here sub interfaces. Interface gig 0x0x0x6.4. Okay.
Hello.
Yes.
Commit after that we need to require that save command in iOS XR.
No need to use save command. That's a different thing. On different iOS we use save command. Okay.
Save your given my command. That's why commit is required enough na for iOS XR.
That is
for
enough.
saving.
This we use in a different iOS, so that was my practice. So that's why I'm.
Okay.
Okay. So we have gig 0x0x6.4. Okay. And then we can say encapsulation .1q we have to use here, and now the VLAN number. So let me use here VLAN 4. Okay. Just say exit. Interface gig 0x0x0x6.5. Encapsulation .1q VLAN 5 we have to use here.
Sir, 1 second.
Yes.
As I'm very new to this iOS XR commands, what it indicates, sir? 0x0x0x6.4. 0x0x6 is 0x0x6 is interface.
Correct.
What is this .4?
Okay, .4 is the interface. Okay.
Sub interface command.
Okay, in one single line card we have sub interfaces.
Yeah, the same line we have to use. So let's say I want to use physical interface. I want to segregate those things, right? So what I can do, just type your interface and then you can that's a 32-bit number. Interface gig 0x0x6 dot. So that's a 32-bit number. Okay. So we can configure n numbers of sub interfaces. Okay. So this 4, it means we are creating a sub interface for this physical gig 0x0x6. Okay.
Okay.
Now,
Sir, one small doubt, one question actually.
uh-huh.
That 6.4 you have given, and that VLAN encapsulation .1Q also you are giving same, and
Mhm.
that both will be the same or it can be different.
Okay, that can be different. That is just for the understanding. That's it. Okay.
That is the virtual link ID, and this is the VLAN number, right?
Correct. Correct. This can be different. This can be different. That doesn't matter. Okay.
Okay, okay.
So we have configured some interfaces. Let me just say commit here. So in the iOS XR, whenever we do any mistake, right, we can see those errors there, right? So everything is fine till this point. Now I will configure some VRF here. VRF. So I will use cust A for this VRF for this customer and same customer B, cust B. Okay. Enter. Exit. VRF. Cust B. Exit. Just say commit. Everything is fine till this point. Now what I will do, I will assign this VRF to those interfaces. Okay. So do show IP route. So I can see here these interfaces we have in the global table right now. Okay. Interface. One more thing, do show IP route. I want to check for the VRF cust A. So I can just say VRF cust A. We do not have anything here. If I'll check this one, no matching routes found, right? So right now, we do not have anything in this VRF. So now I will put gig 0 by 0 by 6.4 VRF cust A IPv4 address. So 15.0.0.1 on /8. So I can use here directly /value, enter, and just say commit. All good. Do show IP route VRF cust A. So yes, now we can see that information. Now let's go to the next interface. Interface gig 0 by 0 by 6.5. Okay. VRF I want to use here. The name of the is VRF is cust B. The IP address I want to use here, you can start with IPv4 address or IP address. Both are same. 16.0.0.1 on /8 and just say commit. Do show IP route VRF cust B. That's it. So now these two interfaces are the part of different VRF and these are different sub interfaces. If I'll check my global table, do show IP route. We do not have those interfaces here in this table because this is a global table, a default table, right? And those are the part of different VRF table. Now, what I will do, I will just run a protocol in between these two devices and in between these two devices just to make the communication that these things are working fine or not. And if these things are working, so if I'll do a ping from here to this address, that should work. If I do a ping from this neighbor to this address, that should work, right? So I will just open R5. I will do a ping from here. 15.0.0.1, that should be reachable. And yes, that is reachable. All good. I'll do a ping from R6. 16.0.0.1 and yes, that is reachable, right? The communication is here. So I'll just run a protocol OSPF. I'll just use 0000. Okay. Now here, I will run OSPF for this VRF. Going to the address family IPv4 unicast VRF. So VRF name is, this is cust B. Area 0 I want to use. Network. So iOS XR, we don't have network command here. So I'll just put here. Oh, yes, we have. I'll just put here interface first of all. We can use network. Oh, sorry. Yeah, we do not have a network command here. We can just change the network type. We do not have a network command like 0012, right? So we can do some mistakes using network command. So I'll just put her interface. So which interface should be the part of this OSPF gig 0 by 0 by 0 by 6.5, enter, and just say commit. Cool. I'll go to R6 and look here. The neighborship is up, right? If I'll check here, do show IP route VRF cust B, we should get that route. And yes, we are getting that route, correct? Now, let me show you the configuration. Do show running configuration router OSPF. So these are the configuration that we have configured here. So if you have any doubt in this configuration, you can ask.
What is address family?
Okay,
IP.
so in iOS XR, whenever we do any task, we have to enable that address family specifically. Okay. If I talk about normal iOS, address family IPv4 is by default enabled. That's why we never run any special command for address family IPv4, right? But for IPv6, for VPN-v4, we run the commands. But in iOS XR, we have to specify the address family also. Okay. That is just enabled to IPv4 unicast. That's it. If this is this interface will be the part of IPv6, then we have to go into the address family IPv6 unicast and have to run the same commands. Okay.
मुझे clear नहीं हुआ है वो address family IPv4 IPv6.
Okay, this is a part that we have done BGP. Okay. So once we start BGP, I'll explain you this one. Okay.
Okay.
Now the next thing, I will run BGP in between these two devices. Okay. Router. Okay, let me start with R5. Router BGP 500. Neighbor. So neighbor is 15001 and remote is 100. I want to advertise a network that is 57.57.57.57/32. That's mask do WR. We go here, router BGP 100. So right now we have to enable our neighborship for VRF. So that's a VPN v4 neighborship, right? So first I'll enable address assembly VPN v4 unicast. So this is a part of BGP. Exit. We have to go into a VRF. That VRF name is cust A. Okay. The neighbor. Okay. So we have to specify the address assembly. First of all, address assembly IPv4 unicast. Exit neighbor.
Router ID not required this command.
Automatically that will take, right?
Hello.
Router ID it will take automatically.
Automatically it will take. Okay.
Yeah. So the neighbor address is 15005. Okay. The remote AS is 500. Okay. And one more thing here, whenever we choose EBG multi-hop. So right now this is on the VRF and we are using iOS XR devices. So we have to configure this EBG multi-hop. So once we put any number here, so it means that will take that specific number. But once I will put directly this command, it will take a default value that is 255. Okay. Now this is done. Address assembly IPv4 unicast. I have to apply a policy. Route policy. Pass in. Pass out. So globally we have to configure that policy. Route policy. Pass everything. Exit. And I'll just say commit. So if we have done some mistakes, we can see the mistakes here. Okay, yeah. Show. Okay, one thing we missed. Look here, if you don't know what you have missed, you can run the command show configuration field. It will show you like what you have done, what mistake you have done. But I remember I have to configure a RD value also here. Okay. So router BGP 100, VRF cust A, RD value is, I'll use here 100. So this is the mandate part. Now if I'll say commit, so now we'll not get any error. Yeah. So let's go to R5 and check the neighborship. Do show IP BGP summary. By default on the iOS XR, the device logs will be disabled, but on the iOS, yes, that is enabled. This will be up. Yeah, the neighborship is up now, right? And the device will start exchanging the route. So if I'll go to iOS XR device, do show IP BGP all. We should get the route. Just wait. Do show IP BGP all summary. Do show BGP all summary. The neighborship is up, but I'm not getting any route. Let's check what is the issue here. We do have some issues. Just wait. Sending a route to this neighbor. That's a BGP neighbor. All good. Neighborship is up also with this neighbor 15001. Router BGP 100. Okay. Address only we have IPv4 unicast. The customer A here we have IPv4 unicast. Address only is enabled. Everything is fine. VRF. First A. Neighbors. Okay, cool. This is the neighbor. Okay, I'm getting a route. No worries. Okay, I was checking a different thing. So I'm getting a route from the neighbor. Okay. Do show IP route VRF trust A, and I can see that route in my BGP table. So right now here on this router, I'm getting a route from this customer A, and if I'll check here also I'm getting a route from the OSPF. So look here, both routers same, exactly same with same slash, right? But I'm getting from a different protocols into a different VRF, and same here getting a different protocol into a different VRF, right? So till this point, everything is fine. Till this point, we have done the configuration. Now I'll do the same thing for this part. Okay, I'll just go to iOS XR 2 device and we'll do the same process. I'll start from R7, R8. Router RIP network 0000. I'll be using here version 2. Okay. Exit. Go to iOS XR device. Router OSPF, sorry, it's RIP. Router RIP VRF trust A neighbor. Interface, I want to put gig 0x0x0x6.4. Okay. Exit and interface gig 0x0x6.4. I will put here receive version 2, send version 2, because we are using here version 2 on R7. That's why I'm using here version 2 specifically. Okay. I will just say commit here. Cool. Now I will enable EIGRP in between 8 and this XR2 device. Okay. Router EIGRP 1 address assembly IP for unit. Okay, so right now we have to go into the VRF. VRF name is first B. Okay. Address assembly IPv4 autonomous system number, that is 1, and we have to specify the not neighbor interface. So interface, that is gig 0x0x6.5. That's it. I'll just say commit here. The neighborship should be up. I'll go to R8. You can see the logs here. Once the neighborship is up. Do show IP EIGRP numbers. Oh, I just did the configuration for the protocols. I have configured VRF and those things, right? Okay, interface gig 0x0x6.4 VRF cust A. Sorry, no. VRF cust A. Encapsulation .1q with VLAN 4. IP address 27002/8. Exit VRF cust A. Exit commit. All good. Interface gig 0x0x6.5 VRF cust B. Encapsulation 5. IP address 2800. And exit. Now VRF cust B. Exit and just say commit. Let's wait for the log. Yep. Neighborship is up. We have queue count, just wait. So if we have queue count here, so we have some issues, just wait. They will negotiate. Okay, now everything is fine. If I go here, do show IP route VRF cust B, I can see the route. Yep, I'm getting the route here. And same here, I'm getting the route from. Okay, so that is sending a summary address. I'll just say router rep no auto summary. Okay, by default auto summary is enabled, that's fine. Now, once we will receive a new update, I will receive 68, 68, 68, 68. No worries, it will receive. Okay, the next task we have done here, it means in between these customers, we have done the configuration, right? And we can see those routes into the routing table also in the iOS XR. Now I will enable IBGP neighborship in between iOS XR1 and iOS XR2. I will enable VPN v4 neighborship in between them. Okay, and yeah, these things I'll use here. First of all, I'll configure IBGP. So I'll start from XR1. Before that, we have to configure the core network, right? The OSPF. So I'll enable OSPF here. Router OSPF 1. address family IPv for unicast. So that's a global base. So I can just directly run the commands network, not network, interfaces, area 0 put here, interface gig 0 by 0 by 1, interface gig 0 by 0 by 3, interface loopback 0 also. Okay, and just put here commit feature. All well. Now I'll go to R4. Router OSPF 1, network 000. This is iOS devices. They will form the neighborship. So just wait for the neighborship with XR1. Neighborship is up here. This will be up. Just wait. Do show IP OSPF interface brief. Let's check what is the issue. We have one neighbor. Okay, I think, yeah, we have received this one. Okay, I think OSPF was pre-configured here. No worries. Okay, so now let's go to this device, XR2. Okay. Router OSPF 1, address assembly IPv for unicast, area 0, interface gig 0 by 0 by 3, 0 by 1, and the main, that is loopback address. And put commit here. Just wait for the load on 4 and 3. Cool, the neighborship is up. Okay. So right now the OSPF, the underlay protocol is up. Right now we can run BGP. I can configure BGP neighborship here. I'll start from R1. Router BGP 100. Address assembly VPN V for unicast. Address assembly VPN V for unicast. Say exit. Now the neighbor. So the neighbor we have to activate, that is 2.2.2.2. Update source, that should be loopback 0. So this is our VPN v4 neighborship. So as I told you in BGP session, for the VPN v4, the next of self is not required. If I'll just talk about IPv4 unicast, right? In that case, yes, we have to specify that please change the next of while sending the packet out to this neighbor. But in the case of VPN v4, there is no requirement of using next of feature. In this case, it will automatically change the next of. Okay. Update source we have done. Now, address family VPN v for unicast, PNV for unicast. Put a route policy, pass in. Okay, route policy is required only for the EBGP neighbor. But still we have configured, no worries. Route policy, already we have passed. Cool. Just say commit here. Okay, we have some issues. Let's check what is the issue here. Show config failed. So using this command, we can check what issue we have done. Neighbor does not exist. Okay. Oh, we have not defined remote AS. Now it's cool. I'll go to this device and we'll do the same process. I'll configure route policy first. Pass everything. Router BGP 100. Address assembly VPN v4 unicast. Say exit. Neighbor is 1.1.1.1.1. Remote AS is 100. Update source is loopback 0. Address assembly VPN v4. Unicast. Route policy pass in. Route policy pass out. So guys, if you have attended the BGP session, so I hope you are aware like what I'm doing here right now, right? Because these things we have done in BGP session, the configuration of BGP. Okay. Exit. Do show BGP all summary. For the VPN v4, this is my router ID and this is my neighbor and the neighborship is up. Well, good. So right now we have the neighborship in between these devices. Right now I just want to exchange the routes from each other. First of all, we should have those routes in the BGP table. So right now what I want here, I want to get the RIP route into BGP table. I want to get the EIGRP route into BGP table. It means what we have to do here, we have to do a redistribution. Okay, now this will be a different kind of redistribution. So we are doing a redistribution from VRF, right? So we have to go into the BGP. We have to say VRF. VRF name is cust A. Address assembly IPv for unicast. Exit. Just wait. VRF cust A. Address assembly IPv for unicast. Redistribute. So what I want to redistribute here, I want to redistribute RIP protocol. The metric, yes, I want to use a metric here. So any metric, yes, 4. That's it. Exit. Just say commit. Issue. Let's check what is the issue here. Cust A, address assembly IPv4. Everything is fine. Oh, we missed the RD value again. RD, let's use 200. That should be unique because whenever the device will put routes into the BGP table, that should be unique. And this RD value make those routes as unique. Cool. Do show IP BGP all. Now I can see that route 68 in the default for VRF custom A, right? For this customer, yes, in BGP we have those routes, right? Now I want to get the customer B routes from BGP into OS, EIGRP into BGP. Okay, exit. Router BGP 100, for which VRF I want to use for cust B. RD value, let me define first, 300:300. Okay, and RD we have done. Address assembly IPv for unicast. Just put the redistribution of EIGRP. One more thing here, whenever we define here, we have to create a route policy. So this is the different metric 4. We have to put a route policy because whenever we do redistribution of EIGRP into, okay, so that is a part of EIGRP. No worries. That is done here. Enter. Okay. Say exit. Commit. All good. Do show IP BGP all. And look here. For the customer A, yes, we have those routes here and those are redistributed routes. And same here for the customer B, we have those routes, the customer B routes, right? So till this point in the BGP, we have those routes. Now I want to exchange these routes to this neighbor. It means I have to put some import export values, right? So I'll go to customer A VRF cust A. Just do one thing, export the routes right now. So we are doing one by one, everything we are doing in the steps. Export address assembly IPv4 unicast, export route target. So export, let me take export to from customer A. So that is 7. So let's put 7:7. Okay. Exit, say commit. Now I will import this value in this VRF. So I'll go here, VRF cust A, address assembly IPv4 unicast, import route target 7:7, say commit. Now we'll see, do show IP BGP all, and look here. I'm getting that route from that neighbor in this customer A, and if I'll check on R5, I'm getting that route. So it means what we have done till this point, the router R7, one path we have done. R7 is sending the route to this way using some VLANs. Using redistribution, we are sending the route to BGP. Using export values, we are sending the route to this table, that is using import value to import the routes, and using again BGP, the device is sending the route to this neighbor. So this path we have done. Now let's work for this path. Okay. So again, I'll start from this device. Okay. So I will go to customer A, customer B VRF cust B, case sensitive, address assembly IPv4 unicast, export route target 8:8. I want to export these routes, right? Just put here commit and go to XR1 device again. Okay. Put here VRF cust B, address assembly IPv4 unicast, and put here import route target 8:8. So once I will put here, it will start receiving the route in the BGP. Commit. Do show IP BGP all. So look here. Okay. Cust B. This is only cust A. Okay, let me check what changes we have done. We have done for cust B. Okay, so I'm getting some routes from here to BGP. We should receive the routes in BGP. Let's check the issue. Show, I think we missed some configuration. Do show running configuration VRF cust B. We are using import value, cool. Do show running configuration router BGP. In the BGP, I will receive the routes. Okay, I have not enabled any cust B here. Okay. Router BGP 100. VRF customer, I have not defined even any RD value. Okay, RD 100, 200, 300. Let me use here 400. Address assembly IPv4 unicast. So right now we don't have a neighbor. Just keep it as it is. Exit. Just say commit. Now it will start receiving the information. Do show IP BGP all. It means just show me everything. Look here. In the customer B, we are getting those routes. Right now, I want to send this route to OSPF now. Earlier that was BGP, so automatically that will reflect the route to another BGP neighbor, to eBGP neighbor. But right now what we have here, we have OSPF domain. So it means we have to do here a redistribution into OSPF. Okay. Router OSPF 1, address assembly IPv for unicast, redistribute. What we have to redistribute? BGP we have to redistribute. The AS number, that is 100. Now, do you want to use any special thing here? So no, I don't want to use, just put a metric here. I'll use here 5. That's it. Just put here commit. Once I will commit here, the device will redistribute all the BGP route that is in VRF. Oh, we missed one thing. We have to put a VRF here first. Then only it will do this redistribution. No redistribute BGP 100. Okay. And put here commit first of all to remove that redistribution. Exit. Router OSPF 1 VRF cust be like this. We have to go address assembly IPv for unicast, redistribute. Now we have to redistribute those routes into this VRF. It means whatever routes we have in customer B VRF, right? Those routes I will redistribute into OSPF customer B VRF. Okay. Redistribute BGP 100 with metric 5. Just put commit here. After this command only, because now we have done the redistribution into the VRF, and yes, we wanted to have this one. Do show IP route, and look here, I'm getting the route. So it means the next part we have done. R7 is sending a end-to-end traffic to R5. R8 is sending a end-to-end traffic to R6. All good. Now we have to do a reverse combination, right? Cool. Now I will try to send the control plane from R5 to R7 and R6 to R8. Okay. So let's check this ISP. Do show IPBGP all. So I'm not getting anything here because we are not using any export value on the other side. Okay, let's go here. Do show IP BGP all. Let's check we have those routes in BGP or not. So in customer A, in cust A, yes, we have that route 57, but in cust B, we do not have that route because that is a part of OSPF yet, right? So I'll just do a thing, router BGP 100, VRF cust B, RD value we have already defined, address assembly IPv for unicast, redistribute. What we have to redistribute? OSPF we have to redistribute. The process number is 1 and the metric, yes, that is 4. You can use any number here, no worries. Just put commit here. Exit. Do show IP BGP all. Now look here. I can see that route in the customer B VRF, right? It means now I can put a value here, a export value. So VRF cust A export address assembly IPv for unicast, export route target. I'll put here 5:5. Okay, exit, put here commit, and go here. VRF cust A and address assembly IPv for unicast, import route target 5:5. So once I'll put these commands, the device will start accepting the routes. Do show IP BGP, just show me all the routes, all the neighborships. So yes, in the customer A, now I'm getting the route, this route, correct? Let's do a redistribution from BGP to RIP now, because now till this point we are getting that route into BGP. Now we have to send the route to RIP protocol. Okay, router RIP VRF cust A, redistribute. What we have to redistribute? BGP. The process number is 100 and the metric. Okay, we don't have any option to use metric here, so just do a redistribution directly. Put here commit. I'll go to R7 and we'll check do show IP route. Yes, I'm getting the route 57. Very good. Now I'll just do it for this route into R8, into EIGRP. So again, go here. VRF name is cust B. Address assembly IPv for unicast. Okay. Now put here export value. Export route target. I'll put here 6:6. Put here commit because we have those routes in the BGP table now. Exit. VRF cust A. Sorry. VRF cust B. Address assembly IPv for unicast. Import route target value, that is 6:6. Put here commit. It means now I will start receiving the route. Till this point, I will receive the route in my BGP table only. Okay, look here. In the customer B, yes, I'm getting the 57 route. Now I want to propagate this route to EIGRP. So basically, whenever we do any redistribution in EIGRP, what we define some metric values: bandwidth, load, delay, reliability, MTU, right? So let me show you first one thing. Router EIGRP, that is 1. VRF cust B. Address assembly IPv for unicast, not unicast. And redistribute. What I want to redistribute? BGP I want to redistribute. AS number is 1. Now, we do not have any option to use a metric value. What we have option to use a route policy. So we have to use a route policy here. So just use a name matrix. I will create now. Okay, go out. If I'll commit here, it will show me your route will not be redistributed. Reason, you are not using any metric value. Okay, so I have to configure route policy. Metric, set EIGRP metric. So now I will start from bandwidth 1000. Then we have delay 1, reliability 255, load 1, MTU 1500, and just put here commit now. All good. I'll go to R8, do show IP route, and look here, I'm getting the route. So end to end, we have these routes, correct? If I do a trace, do trace 57.57.57.57 using source loopback 0 numeric. Look here, I'm getting nothing. It means we have some issues here, right? The next up issue. So let's enable MPLS now. So we have iOS devices, we have iOS XR devices. So now the real thing we have to enable, the MPLS we have to enable here. Okay. So on iOS XR, on iOS devices, I will show you. So we have OSPF here. So I'll use router OSPF 1 MPLS LDP auto config area 0. I'll just go to R3, router OSPF 1 MPLS LDP auto config area 0. All go till this point. Now we have to go to the XR devices to enable MPLS. So on R2, I will show you interface based MPLS. On R1, I will show you OSPF based MPLS. MPLS LDP. Okay. Address assembly IPv for unicast, not unicast. Interface. MPLS LDP. Okay, directly interface. So interface we have gig 0x0x3, 0x3, and interface we have gig 0x0x1. I'll just put here commit. Once I will commit here, I can go to R4 and R3 to see the status. Look here, LDP neighborship is 1. Here it will be up. The neighborship is up, right? Even here I can see the status, do show MPLS LDP neighbors, how many neighbors we have. So I can see one neighbor we have, that is 3.3.3.3 with port 0, and same here we have another one. And one more thing here, as I told you, one TCP session here, we have TCP connection with this neighbor, and look here, we are using port number 646 as I told you, right? Now, okay, so I'll go to this device now and will enable MPLS using OSPF. Router OSPF 1, I want to put it for area 0. MPLS LDP auto config. So this we have enabled in the MPL, in the OSPF, but globally we have to enable MPLS LDP. That is required. Commit. Just few seconds, it will form a neighborship. Do show MPLS LDP neighbor. Yes, one neighbor we have that is 3, one neighbor we have that is 4. Okay. Now I'll show you one thing. I'll go to R4 first of all. Do show MPLS forwarding table. So look here. Local label 16, 17, 18, 19, 20. Because I don't have those routes. Like 3 is the route of R3. This is the route of R3. 1.1.1.1 is the route of R1. 23 and 13 is a subnet that is in between 3 and 2. And 2 is the loopback address of R2. So the device is originating labels. Local labels 16, 17, 18, 19, 20. As I told you, the normal iOS devices start from 16, 17, 18, 19, 20. But the iOS XR devices starts from a different range. Do show MPLS LDP forwarding table. So they are starting from 24004, 5, 6, 7, like 8. Like this they are originating. Okay. Again, I'll go back to R4. So as you can see, I have a label. This is the prefix 1.1.1.1.1, right? And the remote label, the outgoing label is pop. It means whenever I will receive any traffic for 1.1.1.1, what I will do, I will pop the label. I will remove the label, right? But for 3, the local label is 16. So whenever I will receive any traffic from the neighbor, the local label will be 16. If that is 16, I will replace with 03 or 04. If that is towards .1, that will be 03. If that is towards .2, that will be 04. Okay, now, next thing. Do show MPLS LDP bindings. So here we have the bindings, all the bindings here we have. So as you can see, this is like a BGP table, we can say. To reach 1.1.1.1.1, I'm getting routes, I'm getting binding from 2 and from 1 also. Okay, the label from 2 I'm getting 24006 and from 1 I'm getting implicit null, that is null label. Okay, so what happens in this condition, the device will check which next hop is the best, like R2 is the best or R1 is the best. So it will check the routing table. Show IP route. To reach 1.1.1.1, R1 is the best, 14001 is the best, correct? So that's why the device will put this label into the forwarding table, right? In the forwarding table, show MPLS LDP forwarding table. So MPLS forwarding table. That's why I can see here only 14001. Okay. So in the binding table, it will be having everything. It will be having all the labels that I'm getting from the remote label, right? So in this table, I can see these are the remote labels. The local label is 17. The remote labels are these one. But what I have to put as a best route, I have to check my routing table. So once they will check the routing table, they will find, okay, gig 3x0 is the best interface. So I have to put this route as my best route in the forwarding table. That's why we can see that route here. Okay, look here in this table, in this fifth table, what we have, the route, the remote or the single remote label, that is best label, how many bytes we have switched, what is the exit interface, and what is the real next hop for that route. So this is how the routers receive all the labels, check the routing table for the best route, and will put the combination in the forwarding table for the best route. Okay, now, so everything is done here. They are generating labels for all the routes. Okay, if I will do a ping now from R8, this trace, that will be successful. So this is successful, right? Okay, I will just capture a packet from this link. Okay, and we'll show you those things. I told you like one will be a label stack, one will not be a label stack, right? Enter. Let's say the ping packet upon this request. So look here. It will add ICMP. Okay, I'll start from here. Ethernet header. Then we have two MPLS header, right? This MPLS header is indicating the bottom of stack is 0. It means this is not the last label. You can have one more label, and then we can see yes, we have one more label, that is this label, right? So this is saying bottom of stack is 1. Yes, this is the last label, and the last label, this label is generated by MPBGP. If I talk about the normal labels, look here. I'll show you one thing. Do show MPLS forwarding table. This is the VRF route. You can see this is the VRF route, and these are the labels generated by MPBGP. If I talk about these labels, these are normal labels using generated by LDP. But if I talk about VRF label, that is generated by MPBGP. Okay, so these labels are generated by MPBGP. Okay, and it means if we have VPN v4 neighborship, then only the devices will generate these labels. Okay, for the end-to-end neighborship. We have a neighborship in between 1 and 2. So these routers will create some labels just to receive the route into the VRF, because using these labels, they will put the route into the correct VRF. So let's say I can see here customer B, right? So if I'll receive a label, this label, what we have to do, I have to put that route into the customer B VRF, or if I'll receive a label, this one, I have to put the route into the customer A VRF. So using these labels, what they do basically, they put the traffic into the correct VRF. Using these labels, they will find the correct VRF where we have to put the traffic. Okay, next thing. The packets we have done, I have checked the packet also. Okay, and yeah, the LDP, as I told you, they will be using a multicast address 224002, and they will be using some port number 646 to send the packet out to each other, and that will be a UDP packet, right? Cool. Now the next thing here. Okay, and okay, just tell me, till this point, any doubt? Next, we'll discuss some new features. Okay, some other features in the same configuration. So just tell me if you have any doubt till this point, you can ask. Any configuration issue, any concept issue, why they are forwarding, how they are forwarding, anything you can ask.
Okay, so for an example, if we wanted to discuss the control plane and data plane separately, then how we can explain this in this scenario?
Okay, right now for the control plane, the forwarding plane, in this scenario, in this case, both paths are same. Okay. If I'll explain how they are exchanging control plane.
But yeah, paths are same, but how it will be on the basis of like protocol label or like on the label basis.
Look here.
So how we can, like, so if someone asks, then how can explain it?
Yeah. We have this route here. Switch is receiving the route, so this is 1 by 1 on VLAN 4. Using the trunk port, they are sending to this router, correct? So that packet will be having label VLAN 4. This device will receive in this VRF, in this interface, and this interface is a part of customer A VRF, right? That will check, do I have any export value or not? So yes, if find, it will check, do I have any VPN v4 IBGP neighbor? Yes, I have. So the device will send the route with those export values to a VPN v4 neighbor. This will check, do I have that VRF customer A? Yes, I have. Do I have that import value 8:8 or 5:5? Yes, I have that value. So I can accept into the BGP, and then this is RIP protocol. So we have to perform a redistribution into RIP, and then finally they will receive the route. So this was about the route, and once this device will try to communicate, they will go to here, we'll go here, and then the device will check, okay, the next neighbor is 1.1.1.1.1. To reach this neighbor, I have to put some labels. One is my VPN, this is my VPN v4 neighbor, so I have to put a VPN v4 label and a IPv4 normal label. So this device will put two labels. One to reach R4, one to reach that VPN v4, because this device will say, okay, use this label to put the route into the correct VRF. Okay, so let's assume that is 2002 and R4 is sending a local label that is 16. So whenever this device will send the information to R4, that will be having 14, bottom of stack 0, 2002, bottom of stack is 1. This device will receive, this will check, okay, this label is associated with the route that is 1.1.1.1.1, and I have to swap with POP, right? Because that's a PHP hop. So it will remove this label and will forward it to this router. This will check, okay, I'm getting a label that is VRF label, so I have to check the VRF. So that belongs to customer A VRF. So now I have to put this route into the correct VRF, that is customer A VRF, and we'll send it to here. Like this they will do. Okay. And same for R8, R5, R6.
So this is what I understand. It is a part of data plane, right?
Yes, correct.
Yeah, whenever this VPN v4 neighborship between this R1 and like this R2 will be forming, so how the packet will be exchanged to establish that VPN v4 neighborship?
Okay, for the VPN v4 neighborship, that is a part of IBGP only. Okay, because in that condition, if I'll talk about the VPN v4 neighborship, okay, that is nothing, that is just a address family, right? Let's say we have this neighbor 1.1.1.1.1, this is a neighbor 2.2.2.2. If I'll talk about IBGP neighborship in IPv4, so what they will do, they will just form a neighborship with hello packets, right? First of all, they will create a TCP session, they will exchange, they will check those states, they will send those BG messages, and in the BG messages, they will exchange the capability. I support IPv4, just enable for IPv4. The same way they will do, they will just say, now we are not IPv4, we are, the capability we are having, that is VPN v4. So enable the neighborship for VPN v4 only. Okay, it means we are now capable to exchange a route that is 96-bit route. Okay, so that's a normal IPv4 neighborship. We're just using a new capability, that is a VPN v4 capability, to exchange a VRF route. That's it, nothing else. Okay, the routes that we exchange in normal IPv4, the same way we are exchanging here, but this time we are exchanging in the VPN v4 capability. That's it. Okay.
Yeah, that is fine, but it is a 96-bit, so MPVGP will be catering this traffic, right?
Yeah, correct, right?
Yeah, so like how, what kind of packet will be exchanging to form that neighborship?
The packets will be same that we have exchanged in the IPv4, normal IPv4. Okay, a normal update packet will be go. Let's say the neighborship is up in between these routers. Okay, and now they want to exchange the update. A normal update packet will be sent from this neighbor to this one. That's it. Okay.
Okay, so I mean, can we break the neighborship and can we capture any packet to see like what information is going in that?
So I'll just remove this neighbor first of all. Okay. So I'll capture both interfaces because we have two best paths to reach 1.1.1.1. So here the device 1.1.1 is sending a packet, but the neighbor is sending a reset packet. You can see, right? The device is trying to send a SYN, but the neighbor is sending a reset. Reason that is not enabled with that neighbor command. Now, I'll just put those commands again. I'll just say commit here. In the background, they will start initiating the packets. Okay. So here, this is a SYN from R1 to R2. R1 is sending one from 2 to 1, that is SYN packet. Okay. Then from R1 is sending a SYN. This is acknowledge only. Okay. SYN, SYNAC, and ACK. This is a three-way handshake. Okay.
Yeah.
SYNAC and ACK. So first of all, they will initiate this TCP three-way handshake. Correct? This is clear.
Yes. Yes. This is clear.
Then they are exchanging open packet. Let me open this open packet. This is from R1 to R2. So in these capabilities, we should find this router first capability. Again, router refresh. Okay, so right now they are exchanging this capability that I'm having this IPv4. This address is my AS number. Length is 4. Support for 4 octet right now. Okay. And we should see the other things also. This capability shows this multi-protocol extension capability that is saying like this is MPBGP. Okay. Now, the packet from R2 to R1. This was the open packet from 1 to 2. Now we'll check the open packet from 2 to 1. This is the open packet from 2 to 1. Okay. The device is again saying this multi-protocol extension capability, right? Label VPN unicast. It means here this is VPN v4 unicast family. And these are the route refresh capabilities that they should have just to refresh the routes. Okay. And after these open packets, they will send the update packet. Look here. So R1 is sending update packet to the neighbor. So let me open this update packet. They will carry some data in this update packet. Path attribute. So path attributes, okay. I'll show the route also. VPN unicast, okay. NLRI, BGP prefix. So look here. This is that information, right? As I told you. So these are the attribute for that one 57, 57, 57, 57. This is the RD value, route distinguisher 100:100, right? And just keep it. Let's check for the next path attribute. This is the origin code for the same. What origin code we have, what AS path we have. Okay, let me check the next update. This is the path attribute. And check the NLRI. Check this network layer reachability information, BG prefix. Again, this is the same with RD value 400, 400. So we have two things now, right? One is having this route belongs to a different VRF. Okay. And this route belongs to a different VRF, correct? 100 we used for the customer A, 400 we used for the customer B. Other routes here we have path attribute, prefix. This is 16 prefix from customer B. And same here, path attribute. Okay, this is nothing. This is a withdrawn route. This is nothing. Yeah. So this is the update packet. Now just tell me your doubt. Is this clear now?
Yeah, this is clear. So this is the new like attribute MP reach NLRI which we are seeing. So this is I mean new introduced route which was not in IBGP. Okay. So on that basis, like MP reach NLRI, this path attribute is helping to forming the neighborship of the MBPGP.
Okay, to forming the neighborship, that's an open packet, right?
Okay, okay. For the update, okay.
Yeah, that is for the update, okay?
Okay, okay, got it.
Like multi-protocol, and you can see labeled VPN Unica, so that is clear, right? And if I talk about the update packet, so this is the update packet that is having these things, okay?
Yeah, I got it. Okay, thank you.
Okay, cool. Any other doubt, guys? I hope this is clear to everyone.
Yes, clear.
Okay.
Yes, Neeraj.
Okay. So guys, if this is not clear, definitely if you have not done BGP, Santosh and Subhash, okay, because almost 90% commands we are using here from BGP, okay. So if BGP is clear, this will be more clear, okay, because we have address assembly here. So the address assembly concept, the address family IPv4, VPN v4, the VRF concept, these things we have done in BGP. Here we are just using combination of everything, okay. So maybe right now this will be a bit confusing, okay, but once you start your BGP, so this will be very much clear, okay. Amit, for you also.
Yes, Neeraj.
Okay, so right now let's talk about a behavior, how the trace route and ping will work in the case of MPLS, okay. First of all, I will talk about ping, how the ping will work in the MPLS domain, and then we'll come to the trace route mechanism. This is my MPLS core. So let's say this device is doing a ping, okay. So the TTL value is, let's say, by default that will be 255, correct? So the device is sending a packet using 10.0.0.0.1 to destination 20.0.0.0.1 with TTL value 255. This is the packet at layer 3, right? So once this device will send the packet to here, R1 will see I am the ingress LSR. And now what I have to do here, I have to put a label here. So it will put a label here. Let's say that is 17. So I'll choose a random port label number. Now it will check what TTL value we have in this case in the IP header. The same it will do copy and paste into MPLS header 255. Okay. The device will send it to R2. Now R2 will check, I'm getting a packet. Now I'll not count this complete IP address. So 10.1, destination is 20.1 and TTL is 255. R2 cannot see these things. Okay. In the layer 2, it is getting 17 and 255. First of all, it will decrement a TTL. So this will be 254. And now it will replace this label with another label that, let's say, that is 16. Whenever R3 will receive now, it will be like 10.1, 20.1 and 255, because right now these routers are not able to check the layer 3. That's why they will not be able to decrement the TTL value of 255. Okay. And then they will add a label, they will check the label. Okay, I'm getting 16 with 254. R3 will do a decrement in this one. That will be 252, right? 253, sorry. And it will replace this label also. So once R4 will receive the information, that will be like 10.1, 20.1, 255, and the MPLS header is having, let's say 18 and 253. All good. Now R4 will see this is a 18 for a device that is last device. I have to do a PHP. Now what it will do? First of all, it will decrement this TTL to 2, right? While receiving the packet. It will check, I have to remove the MPLS header. Now, it will just do one thing. First of all, before removing this one, it will just do copy and paste this into this one. It means now this 255 will be replaced with 252 and this will be removed. So once R5 will receive the packet, that will be 10.1, 20.1 and that will be 252. So like this, 20.1 will receive the packet. Okay. So this is how the ping will work in the case of MPLS. It means the ingress LSR will do copy and paste into MPLS, but the egress LSR will do copy and paste into IP header. Okay. So this is how the ping works in the MPLS core. Any doubt in this condition? Any doubt if you have, guys?
Can you repeat
No,
once, please, Neeraj?
Yeah, sure.
If you don't.
We have R1,
Yeah.
we have R2, we have R3, we have R4, and we have one user that is having subnet 20.0.0.1. We have a user that is having a subnet of 10. Okay. So this is my MPLS core. Whenever this device will originate a packet, ICMP packet, 10.1 will be the source, 20.1 will be the destination, and the TTL will be 255. So it will start from 255. And R1 will receive the packet, it will decrement it to 254. So once R1 will receive, this will be 254, correct? So R1 will create a packet like 10.1, 20.1, and 254. It will check, okay, I am the ingress LSR. I have to put a new header. I have to put a new label. So let's assume the label is 619. It will add a label 19. It will check, okay, I have one more thing that is TTL value. So I have to do copy and paste into MPLS 254 and will forward it to R2. Once R2 will receive, it will decrement a TTL and will replace the label. Let's say that is 16. This information will be same. R2 will receive 10.1, 20.1, 254 will replace, it will send 16 and 253. R3 will receive, what it will do? Decrement 1 will change the label to, let's say that is 20 now. Once R3 will send further 10.1, 20.1, 254, and this is the label that it is getting 20 with the TTL 252. It will check, now I have to send the route further to R4. That's a PHP router. So what I have to do now, I have to remove the label. But before removing, it will do one task. It will replace the TTL value here. So it will put here 252. It means once R3 will send the route to the traffic to R4, the source will be 20.1, the 10.1, the destination will be 20.1, and the TTL will be 252. And like this, it will send the packet further. So like this, the MPLS works in this code. Okay.
Yeah, got it. Thank you.
Now, we have more things in the ping packet also. How if we, let's say, so in this case, what will happen here? If we have 200 routers here, 255 routers here, so the packet will be discarded. But no, we have a different mechanism for this one. Okay, I'll explain later. Now we'll discuss how Traceroute works in the case of this one. Okay, R1, R2, R3, R4, and R5, and finally that hop that is 20.1, and that hop that is 10.1. So this 10.1 will originate a packet with a TTL count 1, right? So it will add IP header with a TTL value 1. So let's say in the IP header the TTL value is 1. So once R1 will receive the packet, it will decrement by 1. That will be 0. It will say TTL expire, right? So whenever a device will send a TTL expire message, that will be using a ICMP packet with TTL value 255. Okay, it will send it to this one, and it will get to know, okay, the next hop is 10.10. I'm getting a reply from 10.10. It will send a new packet with TTL2. R1 will decrement by 1. It will be 1. Right, now it can send to further R2. Now the IP header is having TTL1, right? It will add MPLS header. It will just do copy and paste a TTL value, as I told you, that is 1. And now I'm not using any IP addresses, the MAC addresses. This is IP header, this is MPLS header. This will send it to R2. Again, R2 will give reply because it will receive 1 minus 1, it will be 0, right? So R1 will receive, even R2 will send the reply with ICMP with TTL 255, cool. R1 will receive, R1 will receive, and will send it to 10.1. It will get to know that I'm getting a reply from 12.2. I have to increase the TTL to 3. It will decrement a 1 once R1 will receive. Again, it will send a new packet. Now look here. In this one, I'm sending a from here 3. It will decrement by 1. It will be 2, right? It will do copy and paste into MPLS. It will receive by 2 in the MPLS, or it will do decrement by 1. Yes, that is 1. It means now this device has a packet with a 2 and packet MPLS with 1. Yes, that can be propagated. So it will send it to R3. R3 will receive with 1 minus 1, that will be 0. That is not propagated. R3 will reply with ICMP with TTL 255. Again, this device will get to know that is 13.3, right? Now it will send by 4. This device will decrement by 1. Now that will be 3. Now, so this device is having a packet 3. Once R2 will receive the packet, it will decrement by 1. So this will be having 3 and 2, correct? It will send it to R3. Once R3 will receive the packet 3, 2 minus 1, that is 1 now, right? Yes, that can be propagated. Once R4 will receive the packet, it will check 1 minus 1, that is 0. That is not routable. Again, it will give reply with 255, 255, 25. It will get to know that is 14.4. It will increase the value again 5 minus 1, right? And again, this will be 4 here on R1. 4 minus 1, that is 3. When R2 will receive, that will be 3. 4 in the IP header. Here is a 3 minus 1, that will be 2. In this case of R3, 4, 2, right? It will receive the packet. It will do a decrement while sending to R4. 4, 1, right? Because it will receive it 2. It will decrement a 1. It will just that 1. I can send the packet out to R5. It will send it to R5 without any label. Now it has to remove a label. What it will do? Again, copy and paste into 4. It means once R5 will receive the packet in the IP header, that will be 1 minus 1, that will be decrement by 0 by 1, and it will be 0, and it will say TTL expire. It will get to know that is 15.5. Like this, it will keep increasing the number and will get reply from last hop. Okay, so this is how Traceroute works in this MPLS code. But now, okay, let me show you in the practical also. I'm doing a trace and I'm getting all the hops. Sometimes what the customer needs, what the ISP needs, I don't want to disclose my addresses. What is my core, how many routers we have, how many labels we are using. I don't want to disclose these things. Okay, so the MPLS routers use, the ISP routers use a mechanism that is propagate TTL mechanism. So I can run a command here, MPLS IP TTL propagate disable, enter. Once I will say commit here, I cannot see the internal path. This is the internal path. I cannot see the internal path. If let's say we have 10 routers in the internal path, I cannot see those 10 internal path, right? And in the background, once we run this command, MPLS IP propagate disable, or if I talk about the iOS routers, we run the command no MPLS IP propagate TTL. So this is the command that we have on the iOS, and this is the command that we have on the iOS XR devices. Okay. So once we run this command, what will happen in the background? The process of ping and trace out will be just opposite then. Okay. How that will be opposite? Now this will be a different ping and different trace out now. Let's say we have R1, we have R2, we have R3, we have R4. Okay. So I'll just discuss trace route. Okay. Because if you get the trace out, so you'll be having knowledge of ICMP also. We have 10.1, we have 10.2. Okay. And it will send a packet with TTL1 first of all. R1 will receive with 1, -1, that will be 0. It will give reply, TTL expire. Cool. Now this device will put 2. And the device will get reply from 10.10. Once it will put 2, R1 will receive with 2 -1. Now it will be 1. Now the packet is propagated. That can be routable, right? It will check. I have to add a new header, MPLS header. Create a packet. IP packet with TTL1. It will check. Once it will create a MPLS header with label and the TTL value. It will check. I have configured a command that is no MPLS IP propagate TTL. Now I cannot propagate this TTL into MPLS header. This one into MPLS header. I cannot propagate. So it will put here 255. So if we will instruct my router that you cannot propagate your TTL, your IP TTL into MPLS, so it will initiate a new TTL with 255. R2 will receive IP with 1. This will be decrement by 254. R3 will receive again 1, 253. This will receive. Now this is the pop router. What it will do? It will try to remove this one. And what is the default mechanism? You have to replace the TTL value. But again, what it will do? It will just remove. It will not replace this one. It will just send it to R4, and R4 will give reply. TTL expires, same. This device will give reply. It means even in the trace route, or if I'll do a ping, these core routers we cannot see. Okay, that's why if I'll talk about ping, if we in the core, if we have, let's suppose 100 routers, and here we have 100 and here we have 100. Now that doesn't matter. Reason, if I start a ping from here 255, that will decrement 100, so this will be 155. But again, from here it will start from IP TTL will be 155, but the MPLS will be 255. So these routers cannot touch this TTL. So till this point I will get 155, and in the IP header that will be 155. These routers will remove this one and will forward it to next one. So now they will decrement 1111. So in this case, yes, if we have multiple routers here, the packet will be propagated if we have more than 255 routers. Okay, so I'll show the practical proof. So I'll run this command now again. I'll remove this command. Okay, I will do a trace and I will do a ping, sorry. I'll open the packet, the request packet I will open. So we can see here, okay, I have to capture both, right? I'll capture this link also, okay. So first I'll show you in the previous example. I can see here in the IP header what TTL we have 254. It will just do copy and paste into this one. That is fine. Okay. Now the next router will just touch the MPLS header. It will not touch the IP header. Okay, this is the different thing. We have to capture a packet in between ISXR1. Look here. In the IP header TTL, that is 254, but in this one, in the MPLS, what we have here, 253, correct? So the devices can just touch the MPLS header TTL, right? They will just do copy and paste like this. And finally, if I will capture this link also, I can see in the real packet, I can see this 253 also. Okay, I can see here 254, where we have 254 in the IP header. This is 254, but once it will again forward it to another router, it will just do copy and paste of the MPLS header. But next thing I will show you, I will run the command. Okay, I will run that command, will enable this feature, commit, and we'll do a ping. And now we'll see the behavior. This is between R3 and ISXR2. In the IP header, look here, what is the TTL value? That is 254. But in the MPLS header, what is the TTL value? 255. Okay, same in other Wireshark. I'll show you here. In the IP header, what is the TTL? That is 254. That is same. But now the device will just decrement this TTL, right? It means if I will enable that feature, the devices will start from 255. But if I disable that feature, it will just do copy and paste of the IP header. So this is how we can originate a packet from outside. And if I want to see the hops, I can disable the feature. If I don't want to see the hops, I can enable the feature. That's it. Okay. So any doubt to this point?
So if you disable the TTL in MPLS, that MPLS route will not going to visible to that customer, right?
Sorry, come again.
Like you disable that MPLS TTL propagation, no?
Right.
So if you'll do that, means that MPLS, ISP routes we can't able to visible from the customer.
Yes, correct. It will originate its new TTL value, a new TTL value. That's why I cannot see those information. Even in the trace route, it will start from 1, but the MPLS router will start from 255, and the 255 will not be expired. That's why we cannot see the TTL value, right? The real hops we cannot see. Okay.
Okay.
Now, one more thing I'll show you how we can configure the indirect neighborship in MPLS. Okay. So first I'll show you how we can run the commands on normal routers. MPLS LDP neighbor. So let's say I'm just using a random command to a random password. If you want to use, you can use a password. Neighbor MPLS LDP neighbor 3.3.3.3 targeted LD. That's it. Okay. I'll do the same on R3. MPLS LDP neighbor 4444, and the password we had used new. MPLS LDP neighbor 4444, and this is my targeted LDP. Look here, the neighborship is up. So this is how we configure indirect neighborship in the case of iOS. Now let's move to the iOS XR. So I'll configure indirect neighborship in between 1 and 2. Do show MPLS LDP neighbor. So as I can see, I have a neighbor that is 3. One neighbor we have that is 4. Okay, now I'll create a new neighbor. MPLS LDP the neighbor. So the neighbor is 1.1.1.1. We have to put a port also 0. Okay. The password. So let me just use a clear password, that is Cisco. Okay. Going to the address assembly IPv4, I have to specify, like here we specify this is the targeted neighbor, right? So by default in normal iOS XR, address assembly IPv4 is enabled, but in normal devices in iOS XR we have to enable address assembly IPv4 neighbor 1.1.1.1. This is my targeted. One more thing, discovering targeted hello accept. Now you can accept your targeted hello. If you receive any hello that is targeted hello, yes, you can accept. Commit. Go to XR1. MPLS LDP neighbor 2.2.2.2. Password neighbor 2.2.2.2. Password clear Cisco address assembly IPv4 neighbor 2.2.2.2 targeted and discovering targeted hello accept. Yes, you are able to access now. Commit. So only these commands we enable, we configure to enable indirect neighborship. So I'll go here on any device I can go, do show MPLS LDP neighbor. So you can see here a neighbor and we can see this is our targeted hello. So this will be unicast. Always the source will be 2.2.2.2, the destination will be 1.1.1.1. Okay. And you can see this is downstream unsoligated. As I told you, this is unsoligated downstream, right? So this neighbor, we have this automatically, they will create some labels, right? And if you want to enable that different feature, that is on demand feature, yes, we can enable MPLS LDP and MPLS LDP, yeah, for the VRF. So cust A, okay, and downstream session downstream on demand. So once I'll press enter here. So using this VRF, whenever it will form any neighborship in MPLS, that will be a always requirement. And finally, with ACL, as I told you, so I can put a ACL here. So whenever it will create a neighborship, MPLS neighborship in this VRF, it will ask for the specific routes. Okay. And this is the solution of MPLS L3VPN. So if you have any doubt, you can ask.
What is the benefit of this indirect LDP neighborship? I mean, why we are forming it?
Okay. For indirect here, let's say I'm configuring indirect here, right? So they will be having some new labels, right? So that will be a direct label. It means if this path goes down, I don't need to exchange the labels, right? Let's say, as I told you, this is the best path, this is the non-best path. So right now I'm using some labels to go via best path. If this path goes down, this device has to again do some calculation to go via the new best path, right? But if we have indirect neighborship, the path doesn't matter which path is available, the device will never execute those configuration, or the device will never they will not run the concept again. Like I have to find the best path, I have to find the best label. The label will be same, but they will just check the path. Okay, this path I have to use now, this path I have to use now. And those things will be done by the normal protocols, not by this LDP. Okay. But if we do not have that indirect neighborship, if this path goes down, LDP will run the mechanism, will find the best path, and best label, and will put in the forwarding table, and will go via then this path. Okay.
Okay, so for an example, we have this indirect neighborship. So what mechanism will be for the new path setup?
Yeah, let's say we just have an indirect neighborship in between these two routers and they're exchanging labels. Okay, and these are just my IGP path. Okay, and that is going via right now this path. Okay, in my routing table the best path is via this way. So once this path goes down, the LDP will not do anything. The routing table will just put a new route, new best route in the routing table via this way, and LDP just use that path to reach that neighbor. Okay.
So how LDP will use this path automatically?
Basically, LDP always check the routing table, right? From the routing table, it will find the best path. Whenever
Yes.
it will be having the binding table, in the binding table also, it will be having a next hop. And that next hop, it will check in the routing table always. Okay.
So like the same thing is happening in this case also, no? Which
No.
which used to be happen in.
Okay.
No.
Look, let's say we have two labels. Label number 10 from here, label number 20 from here. Okay. This is in the binding table. One is 10, one is 20, and this is the best, so the device will put in the forwarding table, that is 10. Okay, but now this goes down. What the device has to do, the device has to run the LDP again, the mechanism again, and have to remove this one and have to put again, go to the binding table, have to check how many paths we are available, and have to put 20 here, correct?
Yes, yes.
Right. And then it will find the best path. But if we have indirect neighborship, in the binding table, I will be having a single label, that is 10, correct? Because I'm getting a label from R1 only, and that will put in the forwarding table, that is 10. Now that doesn't matter what next hop we have. If next hop is available via this way, the device will choose this path. If this goes down, that will go via another path from the routing table. It will never change the label. Okay, it means it will never do any lookup in the binding table again, because my LDP session is up with my neighbor, so I don't need to do anything. I just have to relay on my routing table. Okay.
Yeah, I mean, I can understand the concept you are telling, but I am not able to understand like how it will be calculating, like, because to calculate the alternate path, it has to be run the mechanism, or like how it will be having that alternate path automatically initial.
If here we have physical interface neighborship and here we have direct neighborship. In the physical,
Yes.
I'll be having two remote labels. One is 10, one is 20. I have to find one as best route, correct?
Yes.
As best label. So if that is 10 goes down, I have to do a recalculation again and have to find the another best label, correct?
Correct, correct.
If we have indirect neighborship, in that case, we have one single label. Okay, and that will remain in my forwarding table now for both. If this path goes down, the device will check a new path. If this path goes down, the device has to check the new path. But in this case, if this path goes down, it will indicate, oh, that neighbor is down. My LDP neighbor is down. If my LDP neighbor is down from here, I have to remove these one and have to run again check. Okay, now we have another label, that is why another LDP neighbor, and have to put in the forwarding table and then go via this path. It means in this case, what is happening here? I'm just checking the routing table to find a new path. But in this case, what I'm doing here, I'm checking my new LDP neighbor and new labels. But here the label will be same, the neighbor will be same. I just have to find a new path. Here I have to find a new label, new neighbor, and new path. Okay.
Okay, okay. So this lookup for the new label, we can save it, right?
Yes, definitely.
This is the benefit. Okay, okay. Okay, got it.
Okay. Guys, any other doubt?
Yeah, actually, one more doubt. I mean, that is not related to this MPLS, but the capture you were showing in that we have the packets, and what is this value? I mean, which is downside, right? Like right now, I can see this frame, Ethernet, and all. But whenever we used to open this packet, can you open anyone?
Yeah.
I mean, when you double click and it used to open, yeah. So what are these value? I mean, are they relevant? Yeah.
So basically, these are the like whenever the device will send the packet out to the LAN Ethernet, right? So these are the combination. That's it, nothing else. hexadecimal format. This is.
Not
That's
to
it.
check these value, right?
No, nothing.
Okay, okay, okay.
These are the
Okay, got
hexadecimal
it.
conversion. Okay.
Okay, okay, okay. Fine, fine.
Any other doubt?
For me now it is
701.
okay.
Okay. And one more command we have that we can run. MPLS LDP notice label 4. So this is a command that we can use to specify the labels for specific route. Let's say we have 100 routes, but I don't want to send the labels for 100 routes. I can just put some specific route and can annotate the labels for those. Okay. One more thing here we have in the iOS XR, MPLS LDP and the summary labels, remote label, local, allocate for host route. So this is how we can originate labels only for the host routes. It means if I find a route that is on /32, it means host route. So yes, for that I will originate. For the transit interfaces, I will not originate. Or if you want to use a ACL, so I can use ACL here to enable or to propagate routes to local routes, local labels for routes that belongs to this ACL. Okay, so this is how we can control the labels for the routes. Okay, and yeah, so these things we have in the case of MPLS. So guys, I'm done from my side. Okay, if you have any doubt, you can ask.
We have to actually do lots of practice regarding that MPLS. So as of now, the theory part and what we have seen in your practical lab, as of now there is no doubt. So as long as we have to, we are not doing any practical, no, we will come to know. We'll never come to know that what is.
Yeah. So just do the practicals again. Just go through the theory again. Okay. So once you'll do the practical, definitely you'll be having some issues, some doubts. Okay, and then you can ask your doubts. Okay.
Related
So,
configuration have provided a workbook.
Sorry.
Workbook.
Hello.
Configuration.
For these things, I'll share this file also to you. Okay. I'll share this diagram.
So Neeraj, do you have this book by Lakshman for the MPLS PDF?
No.
For theory also required. Practice theory.
Actually, Neeraj here. Actually, last 2 days back, actually, I tried to install that iOS XR, but it's not installing properly. It's showing some error. By the time I'm booting, actually, it is stuck in somewhere in the middle.
Okay, but I can check, but I don't have much idea about this GNS3, how we can resolve those errors. Okay, so in the free time we can set, but no worries. Okay.
Okay.
So I think all
So
of
are
you.
we covering this community last lecture you discussed about?
The communities, extended communities, right? Which you're talking about?
I'll discuss regarding
Yeah, in BGP. Yeah, BGP. You like in last class you discussed like we will be covering this communities thing in next class.
Okay. Yeah, we can discuss right now, no problem. Okay.
And regular expression about
regular expressions, I think we did last time. The class we did on the regular expressions. Okay, for the communities, yeah, we did that thing. And for the communities, that will not take so much time. Okay, we have two types of communities. Okay, one is standard and one is extended. So right now we have done one thing, that is VPN v4, right? So in that one, I told you one thing. By default, extended communities are not enabled, right? Remember? So by default,
extended community like this MPBGP, right?
Right. If I talk about RD, right, that is a part of extended communities. Okay, so basically communities, we can say those are the type of tag that we use with the labels to exchange to the neighbor. We have two types of communities. One is standard and one is extended. Extended, it means the device will originate the information, or let's say if I talk about RD value, RT value, these things, these are the part of extended. If I talk about standard, we have some well-known communities and we have some custom communities, we can say. Custom communities, it means we can configure some tag, we can bind with the values, with the routes, and we can do some manipulation. Okay, that is again a part of filtering. So let me take an example first. Let's say we have R1 here, we have R2 here, and we have R3, R4, and R5. Okay, so let's say this has some routes. Same, the device is having those routes. Okay, maybe this is the same domain. So now what I want here, for these routers, I want to do a filtering, and kind of filtering we can say. Okay, so whenever this router will try to communicate to 3.3.3.3, the best path should be via R4. And whenever the device try to communicate to 4.4.4.4, the best path should be via R5. And I want to achieve these things using standard communities. Okay. Now, what we can do here, we can say to R4, first of all, I have to specify that to this neighbor, you can send your communities. I have to specify, enable that feature. Same here. For this neighbor, you can send your communities. Okay, now I will create a ACL here. We'll create a route map. So let's say ACL for this route 3.3.3.3. I will call this ACL into this route map and we'll put here set community 1:1, let's say. Okay, and 4.4.4.4, I will put here community, let's say ACL. I will call this route and will put a route map with this ACL with community 2:2. So now these routers will receive the communities. So whenever R2 will receive the route 3:3.3.3.3, it will be having 1:1. I can see these things in the BGP table also. Okay, now we can decide what to do with these communities. I can say here, whenever I will receive a community 1:1, just do one thing. Set up local preference value, that is 110. Same here, I can say to R3, whenever you will receive a community value 2:2, just do one thing, set a preference value, local preference value 110. So any kind of filtering we can put. It means now we are doing a filtering on the behalf of a community. Community, it means 1:1, 2:2. So these are the kind of tag that we are using here. Okay, and we can put origin code, local preference, AS path, any kind of attribute we can use with these things. Okay, so this is the concept of communities that we use to do a filtering to manipulate the path. So just tell me, any doubt in this one, in the concept?
Okay, so what I understand from this concept, on the basis of the community, we also define the original like BGP path attribute or these things, right?
Yes,
I mean,
yes.
if we are matching some community and maybe we are getting a local preference higher for that, But if you wanted to prefer the path on which local preference is lower, and here the local preference can I mean select the part, but on the basis of community we can also define that local path preference rule, right?
Correct. Right.
Okay.
Absolutely correct. Okay. So basically, if I talk about, let's say, in EIGRP, we have tag value. Remember, in EIGRP, we set a tag, and using that tag, we do a tag-based filtering. Correct. Same here, we have communities. It means we have a tag value in the BGP route, and using that tag, we can do anything. It means we can do any kind of filtering, any kind of manipulation, route manipulation we can do. Okay. So the concept behind the communities, that is clear.
Yes, the concept is clear.
Okay, now I'll just do this one. I'll just do a practical. Okay. Just wait. Can you see my diagram? Hello?
Yes.
Okay. Just hold on. Just hold on. Okay, so let me just remove previous configuration if we have anything. Okay, so first of all, I will configure IBGP, EBGP neighborship here. Okay, I'll just do the configuration for IBGP, EBGP. Router BGP 1, that's right. Now this my ABGP neighbor remote is 2. Neighbor 34003 remote is 3. Router BGP 2 neighbor 12001 remote is 123, router BGP3, neighbor 34004, remote is 123. Okay, the neighborship is up, right? Now let me check, do we have some routes or not? Do show IP interface brief 2 and 3. Do show IP interface brief 2 and 3. Okay, cool. So what I'll do here, first of all, I will advertise network 2.2.2.2 mask 245.245.255 and 3 also. The same I will do on the next router, that is R3, that has the same routes, right? And let's check we are getting the route till R5 or not. Do show IP BGP. So I'm getting 3, I'll receive, just wait. Okay, perfect. 3, it should receive via another router also. Just wait. 2 I'm getting from 1 and 4. 3 I'm getting only from 1, not from 4. Maybe we can have some issues. It should receive. Yeah, now we are getting the route. Okay, but that is best. Okay, so do show IP BGP 2.2.2.2.2. Can anyone tell me why that route is best via R1, not via R4?
Local preference value? No, sorry, no.
Okay, because of router ID. Okay.
Okay.
Now let's move. I will indicate R2. Whenever you will advertise a route 2.2.2.2, use a community value 1. For 333, use a community value 2, and same for R3 I'll do. Access list 1, permit 2.2.2.2, 0000. Access list 2, permit 333.0.0.0. I'll configure route map, com, match IP address 1, set community 1. Okay, exit with the higher sequence number 20, match IP address 1. Oh, sorry. Match IP address 2 because I have to match the second ACL, and set community 2. Okay, do show history. I'll just do copy and paste. Pipe section access list and route map. Okay. Now I'll say router BGP to neighbor 12.0.0.1 send community both. Okay, and neighbor 12.0.0.1, I'll put a route map here. Route map name is com, I think. Yeah, in out direction, and do clear IP route star soft. The same commands we run in the case of iOS XRO. Okay, do show IP. The soft keyword works there. We'll go to R3, router BGP 3, and neighbor we have 34.0.0.4, send community both. Okay, and neighbor 34.0.0.4, route map com in out direction do clear IP BGP star soft. Cool. Now we can go to R1, R4 and can check the community. So I'm getting around 2.2.2 and 3. So let's check that information. So I can see here I'm getting a community 1. Let's check it for 3. Yes, I'm getting a community 2. Right or wrong? Any doubt in this condition? Any doubt? If you have, just tell me.
No, it is clear.
Okay. Now I will match this community and will call into a new community IP, because now this is my IGP domain. I have to send the information to the towards the neighbor and have to set the conditions, right? Community list. So I can use a number from 1 to any number, right? This is expanded range, not extended. So any number I can use here. 1. So permit what I want to match. The community 1 I want to match here. 1. Okay. About these things I'll discuss later. What are these communities? And IP community list 2. What I want to match here? The community 2 I want to match. The same task I'll do on another router. Do show history. So I'll just do one by one. Do show IP BGP 2.2.2.2. Community 1 I'm getting here, and for 3 I'm getting this community 2. Done. So till this point what we have done, we have called a community, right, into IP community list 1. So those community lists I can call into a route map basically. That's why we have configured these community list. Okay. Now route map, let's say LP match community. So now we have to call that community list. That's why we have to configure community list. If I'll get a option to directly call a community, so I can just directly put the community here. But right now we don't have any option to call that community directly. That's why we have to use community list number. So list number 1. Okay. And set local preference. Let's put here 110. Exit. Okay. I'll just do here. So I'll just put 110 with 1 and here 110 with 2. Okay. So route map we have done LP, all good. One more route map we have to configure just to receive other routes, right? Name is LP. Neighbor 12002. Route map LP. We are on R4, sorry. Neighbor 34003. Route map LP N. Do clear IP BGP star soft. Do show IP BGP. You can see using community only we are setting a local preference. I'll just do the same task on R1. Okay. Route map LP match community list 2, set local preference 110. Okay, and just say exit. Put a higher sequence number just to permit other routes. Router BGP 123, neighbor 12002, route map LP, direction is in, just clear the process. Cool. I'll go to now R5. So look here. Now to reach 2.2.2.2, which is the best path, that is via 4, and to reach 333, which is the best path, that is via R1. So right now what we have done here, we have done a path manipulation using communities. Okay. So any doubt till this point? Like this, we can use communities, but we never use communities, right? We have path attributes directly. We can call the route and can use the path attributes to do the manipulation. So this is just another way to do the filtering. Okay. So any doubt till this point, guys?
It is, yeah, clear.
Okay. Now I'll explain you the other communities. The well-known communities basically. What we can do, let's say we are getting some routes from the internet. So what I can do there, just to get a category, right? Just to check those routes belongs to my internet or not. I can put a category, I can put a community that is internet community. That's it. This is again, this is just a tag value. Okay. But now the next is local AS. If I choose local AS, it means, let's say I'm getting a route. So first of all, let me show you here. The device is saying do not send outside local AS. Okay. So I hope you remember the local AS feature. Remember? Now, so if that is local AS, it means, let's say I'm getting a route from a neighbor on a router, and I'm using, with that neighbor, I'm using a local AS community. It means I will match those routes and will set community local AS. In this condition, what will happen here? What is the meaning of this AS with this local AS feature? That route will be remains in the local AS only. It means that route will be advertised only to the local AS, not beyond to the local AS. The same the device is saying, do not send outside local AS. Okay. Now, the next is no advertise. Okay. Let's say we have R1 here, we have R2, and we have R3. R1 is getting a route 1.1.1.1 route, 1.1.1.2 route. These two routes the device is getting. So the device will put a community. Let's say it will put here no advertise with this route and is sending to this neighbor. So it will receive the route. Okay, that is 1.1.1.1 route with a community that is no advertise. It means do not advertise to any peer. It means I will not be advertised to a EBG peer. I will not be advertised to any IBG peer. Okay. The next is no export. Let me show you this one, the line. No advertise. Do not advertise to any peer. It means whenever I will receive a packet with the community, no advertise, it means I will not be able to advertise that route to any neighbor, any kind of neighbor. Okay. But no export is a bit different. This community, if let's say the same diagram we have R1, R2 and R3. R1 is getting that information 1.1.1.1.1 with no export community. It means that route will remains in the same AS. It means these routers will not be able to advertise that route to another AS. The same here we have do not export the route to next AS. It means till this AS, yes, we can have that route. R2 can have that route. R3 can use that route, but these routers will not be able to exchange the route to another AS. So that's it. These are the well-known communities and the custom that we use 1, 2, 3 to manipulate the path. So guys, tell me, any doubt? Anyone? Any doubt?
Yeah, so far is not actually. Maybe after the doing some practicals.
Sure, no worries. Just do the practicals, okay, and check theory part also. If you face any doubt, just ping me on the WhatsApp or call me. Okay. So let's wind up here the session. Okay, and I hope the MPLS is more clear, right, to everyone.
Yes.
Okay, perfect. Again, if you face any doubt, any practical issue, okay, just ping me over the WhatsApp or call me. Okay, if I'll be free, I'll definitely help you. Okay.
Sure. Okay. Thanks. So can you please check if you find this MPLS by Umesh Lakshman, because somebody recommended he has hard copy, but that is very expensive. So if you found the PDF for this,
The name you're saying, what was the name?
Umesh Lakshman MPLS for MPLS.
Umesh Lakshman, right?
Yes. Yes. Yes.
Okay. Okay, I'll check. Okay, guys. Bye.
Okay. Thank you so much. Bye. Bye.
Okay, thank you so much. Okay, sir.
Okay, sir. Thank you.
Bye.
Bye.